Hello there and welcome to Physics with William, where curiosity gets comfortable and difficult ideas are given enough time to unfold without hurrying anyone along. Tonight we're going to spend a little while with one of those results in mathematics that sounds like a joke the first time you hear it and then slowly becomes stranger the more seriously you take it. It is called the hairy ball theorem, which is a name so cheerfully undignified that it almost seems designed to lower your guard. You hear it and think of a tennis ball that has had a rough week, or perhaps a very determined peach, or some unfortunate little creature who has just woken up from a nap and is refusing all attempts at grooming. But hidden inside that silly name is a statement about shape, motion, surfaces, and the quiet stubbornness of geometry. Before we get into that, I would love to know where in the world you're listening from tonight, and what sort of hour it is in your corner of things. Are you hearing this late in the evening after the day has finally stopped asking things of you? Is it early morning, with the room still dim and the mind not yet fully persuaded to begin? Or perhaps it is the middle of the afternoon and you have simply decided that a theorem about hair and spheres is exactly the kind of company you need. Wherever you are, I am glad you are here. And if this little journey turns out to be soothing or interesting, or just a pleasant way to wind down while your thoughts loosen their grip on the day, I would be very grateful if you liked the video and perhaps subscribed as well. It helps this quiet corner of science reach other people who may also enjoy being gently talked into a mathematical puzzle, while the rest of the world carries on being noisy elsewhere. Now, the theorem itself says something very specific and very odd. If you have a sphere covered in hair, and you try to comb all of that hair flat without creating any tuft, swirl, spike, or bald oddity where the direction breaks down, you cannot do it. Somewhere on that sphere there must be at least one point where the hair refuses to lie neatly in a clean direction. Somewhere there must be a cowlick, a whirl, a still point, or a place where your combing simply cannot continue in the same tidy way. In loose everyday terms, you cannot comb a hairy ball flat. That sounds harmless enough at first. You might even think, well yes, of course. Spheres are awkward. They roll away. They resist organisation. Anyone who has ever tried to wrap a present shaped like an orange knows that curves have opinions. But the remarkable thing here is that this is not a practical observation about difficult grooming. It is not merely saying that combing a hairy cricket ball would be inconvenient. It is saying that there is a deep structural reason this cannot be done. The obstacle is built into the shape itself, and that is what makes results like this so satisfying. They take a familiar object, something almost embarrassingly ordinary, and reveal that it has been carrying a hidden law all along. A sphere seems so innocent. It is the sort of shape children draw without thinking much about it. It appears in bubbles, planets, marbles, fruit, droplets, eyes, beads, bearings, ornaments, and all those little diagrams people make when they want to suggest something complete and self-contained. The sphere has a reputation for being simple, balanced, polite, symmetrical. And yet here it is, quietly refusing to let its imaginary hair behave. That refusal tells us something important. In mathematics, the deepest constraints are often not visible in the way a thing looks, but in the way a thing is connected. Two shapes may seem different and yet share the same underlying character, or they may seem alike in their smoothness and roundness, while one contains a hidden possibility that the other completely lacks. That is the territory we are heading toward. We are not only talking about hair, obviously. We are talking about directions on surfaces, about the difference between local order and global order, about how something can look manageable in every small patch, and still resist being organised all at once. The reason this becomes so memorable is that it attaches a serious idea to a ridiculous image. Mathematics is actually rather good at that. It has a gift for making the abstract cling to something concrete. You might struggle to remember a dry statement about continuous tangent vector fields on even dimensional spheres, but tell someone that a hairy ball cannot be combed flat and suddenly the whole matter becomes difficult to forget. The image does part of the work for you. You can picture it. You can feel the problem in your hands. You can imagine turning the sphere this way and that, trying once again to smooth every strand into obedience, only to find that somewhere the pattern collapses into a stubborn little uprising. That may be one reason people love the theorem. It lets you enter a real mathematical idea through an ordinary act. You do not need years of training to feel why the claim is interesting. You only need to understand what it means to try to make everything line up, and to discover that the attempt fails not because you are clumsy, but because the world has drawn a line and said no further. There is also something unexpectedly comforting about that. Much of life is spent smoothing things, arranging them, trying to get every part of a complicated situation to settle into neat alignment. We straighten schedules, tidy rooms, organize plans, revise conversations in our heads, and generally act as though with enough patience, the whole mess of existence might eventually behave like a well-folded shirt. Then some small stubborn fact appears and reminds us that not every kind of disorder is a mistake. Some are structural, some are not signs that we have failed, but signs that the thing itself was never meant to be perfectly flattened. This does not mean the theorem is philosophical in the vague, hand-waving sense that sometimes hovers over mathematics documentaries like a scented candle no one asked for. It is precise, it is technical, it is provable. But it does have that rare quality some mathematical ideas possess, where the truth feels useful beyond the formal setting because it reminds us that shape matters, structure matters, and not every problem can be solved by more effort applied in the same direction. To begin getting comfortable with the idea, it helps to think about what hair stands in for here. Real hair is messy, variable, and not always cooperative even on a human head, where evolution at least gave it a reasonable amount of room to negotiate. On a sphere, in the setting of the theorem, the hair represents a direction assigned at each point on the surface. Imagine that at every tiny location on the sphere you place a small arrow that lies flat along the surface. Not sticking outward, not poking inward, but lying smoothly along the skin of the sphere, as though each arrow were a little strand being combed in some direction. You would like to do this everywhere without interruption. You would like every strand to have a direction, and you would like those directions to vary smoothly from one point to the next. No sudden jumps, no tears, no places where the rule breaks. The theorem says that on a sphere you cannot manage it. Somewhere, at least one point must be left with no clean direction at all. Somewhere the arrow has to vanish, or the hair has to stand in a confused whirl, or the pattern must fail in a way that cannot be repaired by patient brushing. If you only look at a tiny patch of the sphere, everything seems fine. A small enough patch is almost flat, and on a flat patch you can happily comb the hair in parallel lines and call it a day. The trouble only appears when you insist on doing this across the whole surface at once. What works locally stops working globally. That local versus global tension is one of the great recurring themes in mathematics. A small area can look simple, a large whole can quietly deny that simplicity. It is the same sort of surprise you get when a road looks straight from where you stand but eventually curves around a hill, or when a map looks harmless until you realise the planet it represents has no actual corners. Small regions let you forget the larger shape. The larger shape eventually collects what you forgot and presents it back to you with interest. This is why spheres are more subtle than they first appear. On a flat table you can draw arrows all pointing east, and nothing dramatic happens. Every point agrees, every direction lines up. The surface does not argue, but a sphere has no single, everywhere consistent version of that arrangement. Try to imitate the same neatness on a globe and the trouble appears slowly. Near one region the arrows seem reasonable. Move along and they begin to bend. Continue further, and you realise that some part of the surface is being asked to satisfy incompatible demands. The shape closes back on itself. There is no edge to hide the problem at, no corner to tuck the difficulty into. The sphere is complete, and so the contradiction has nowhere to go except into a point of failure. That point of failure is not some embarrassing exception the theorem grudgingly tolerates. It is the whole point. The theorem is telling you that the failure is necessary, not accidental, not due to poor design, and not removable by a more clever barber. You can already see why the Earth becomes one of the favourite examples. Imagine the wind at every point on the surface of the Earth. At each location, the wind blows in some direction across the ground. Those directions change from place to place, but suppose for a moment that the wind is behaving smoothly, with no abrupt jumps. Then the hairy ball theorem tells you that there must be at least one point on Earth where the horizontal wind is zero, some place where, at least at that instant, the air is still. Not because weather forecasters need a dramatic pause, but because the spherical shape of the planet forces such a point to exist if the wind field is smooth enough. In a strangely elegant way, the theorem turns an abstract statement about tangent directions into a claim about calm spots in the atmosphere. And suddenly, the hairy ball is no longer merely a comic object. It is the Earth. Or rather, the Earth as a surface carrying directional information. Once you see that, the whole subject becomes broader. Hair on a sphere, wind on a planet, flow along a surface, alignment without singularity. These are all versions of the same question. Can you assign a smooth direction everywhere on a shape without anything breaking down? On some shapes, yes. On a sphere, no. Now, if you're listening in a pleasantly drowsy state and wondering whether this is one of those moments where mathematics begins with combing and ends 3 minutes later, in a blizzard of terminology, rest easy. We are not going to sprint into formality. There is plenty of time for the deeper structure to reveal itself gradually. The best way into ideas like this is not by beginning at full abstraction, but by staying with the image long enough that the abstraction begins to feel natural. So let us stay with the comb for a moment. Imagine holding a perfectly furry orange. Not real orange, obviously, unless your local supermarket has become far more adventurous than most. A smooth sphere, densely covered in little soft strands. You place a comb against it and begin brushing. On the front-facing patch, everything goes well, the strands align. You move the comb slightly and continue. Still fine. You rotate the sphere in your hand and carry on. The order spreads. It feels promising. Surely, you think, this is just a matter of patience. But then some region begins to resist. The strands cannot all keep the same sort of alignment as the surface curves around. To settle one region cleanly is to introduce strain somewhere else. Smooth one side and another develops a swirl. Chase the swirl away and it reappears elsewhere. The problem migrates, but it does not disappear. It is as though the sphere is politely insisting that one patch of disobedience be preserved. If you have ever dealt with bed hair, sweater fibres, paint strokes, grass flattened by wind, or a carpet that looks one colour from one angle and another from the opposite direction, you already know something about directional texture. Much of the visible world is full of surfaces that carry local alignment. Leaves have grain, fur has lay, sand has ripples, brushed metal has a texture that depends on direction. In each case, the direction matters, and the geometry of the surface matters too. Usually we do not ask the fully global question. Usually it is enough that the local patch behaves. The hairy ball theorem is what happens when mathematics politely refuses to stop at local convenience and asks whether the arrangement can be made consistent everywhere. It is a very mathematical sort of persistence. The mathematician looks at the nearly combed sphere and says, "That looks fine near here, but what about the entire surface?" The ordinary rest of us tend to say, "Near here is probably enough." This difference in temperament is one of the reasons mathematics discovers such strange truths. It does not accept partial success when the question is global. It keeps asking whether the neat picture really holds all the way around, and often the answer is no. Not because reality is malicious, but because reality has structure. The structure of the sphere matters more than the flexibility of your imagined hair. This is an important point, because it helps us see that the theorem is not about materials. It is not about stiffness or friction or static electricity or poor grooming choices. It is about the geometry and topology of the surface. If the sphere were made of velvet or steel or moonlight or patient mathematical imagination, the underlying restriction would remain the same. There is another reason this theorem makes such a strong first impression. It sits right at the boundary between the visual and the conceptual. You can picture it, but the reason it must be true is not immediately visible in one glance. Many mathematical facts are either too obvious to be interesting or too technical to feel intuitive at first. This one occupies a sweet spot. The statement is accessible. The inevitability is not. That gap is where curiosity lives, and curiosity in subjects like this is usually more useful than haste. If you rush too quickly to the finished statement, you miss the pleasure of watching the simple picture acquire depth. The point is not merely to know that a hairy ball cannot be combed flat. The point is to understand why such a silly sentence manages to describe a serious and far-reaching piece of mathematics. The point is to feel how a sphere can hide a constraint that only becomes visible when you ask the right question. In that sense, the theorem is also a lesson in how mathematics often works. It does not only count things or measure things, it studies possibility. It asks what arrangements are allowed in principle, long before anyone starts computing details. Can this shape support that pattern? Can this surface host that kind of flow? Can this local rule be extended globally? These are structural questions, and their answers often arrive with an air of quiet finality. Not difficult, impossible, not inconvenient, forbidden. That can sound severe, but it is also clarifying. Once you know a thing cannot be done, you stop spending energy trying to force it. You start asking better questions instead. If a sphere cannot be combed flat everywhere, where must the trouble show up? How many singular points can there be? Can they move? Can they cancel? What happens on other shapes? What if the surface has a hole? What if it is not a sphere at all? Those questions are where the subject begins to open, and that is where we're going next. Because before we can appreciate why the sphere must keep at least one unruly spot, we need to understand what kind of mathematics notices such a thing in the first place. We need to talk about the branch of mathematics that cares less about exact lengths and angles, and more about the deeper character of a shape, the kind of character that survives stretching, bending, and gentle deformation. In other words, to understand why a hairy ball cannot be tamed, it helps to look at what a surface really is when mathematics stops judging it by appearance alone. Let us keep that oddly furry sphere in hand a little longer, because the easiest way to miss what makes the hairy ball theorem interesting is to rush straight to the formal statement and leave behind the everyday instinct that gives it life. Most theorems do not begin in the bathroom mirror, but this one very nearly does. It begins in the simple act of trying to make something lie neatly in one direction, and discovering that the surface underneath has other ideas. Picture the scene properly. It is morning. Perhaps not your best morning, but one of those ordinary ones where the mind is still working its way toward coherence. A brush is found, a comb is selected, a small domestic campaign begins against disorder. Hair, as it turns out, is never entirely neutral about these matters. Some of it cooperates out of habit, some of it gives in temporarily, only to reverse its decision at the first opportunity. And some small region, usually hidden until the last moment, has spent the night preparing a local rebellion. No amount of patience seems to persuade it that the rest of the arrangement is settled. That little rebellion is not, of course, a proof of a theorem. Mathematics is not in the business of approving every cowlick as a deep truth about the universe, but the experience is useful because it teaches a physical lesson first. Surfaces matter, direction matters, and trying to organize many tiny directions at once can be more complicated than it first appears. On a human head, the reasons are biological and messy. Hair grows from follicles angled in different ways. The scalp is not a perfect surface. Moisture, sleep, pressure, and the occasional indifference of genetics all play their part. There is no single clean geometric law governing every difficult patch. Real hair is a negotiation between anatomy and weather, with occasional contributions from poor life choices. But mathematics likes to simplify just enough to expose the structure beneath the clutter. It says, Let us forget shampoo and sleep positions and split ends. Let us imagine an ideal sphere covered in ideal hairs, each hair lying flat against the surface, and ask whether all of them can be arranged smoothly at once. That imagined morning struggle is where the theorem becomes easier to feel, not yet to prove, but to feel. Because the challenge is not merely one of local grooming, any small patch can be managed. That is important. If you zoom in on a tiny region of the sphere, it starts to look almost flat. And on an almost flat patch, everything seems easy. You can brush the hairs to the left or to the right, or diagonally, and every strand seems satisfied. There is no obvious problem. If all you ever saw were little patches, you might conclude that the whole surface should pose no serious difficulty. After all, each part behaves. Why should the whole not do the same? The answer is that a whole surface is not just a pile of small patches. A whole surface carries global structure. Each local arrangement has to fit with its neighbours, and then with the neighbours of those neighbours, and eventually with distant regions you thought had nothing to do with the first decision. The sphere closes around itself. It has no boundary where a mismatch can quietly escape. It has no edge where you can say the pattern simply stops. Every local choice is part of a larger demand for consistency, and it is that larger demand that causes trouble. This is one of the great differences between dealing with a flat plane and dealing with a curved closed surface. On a flat tabletop, for instance, you can imagine drawing tiny arrows everywhere, all pointing east. Nothing dramatic happens. The arrows agree with one another. No point is forced into indecision. If you covered the table in short fur and brushed it all eastward, the table would not object. A table is generous in this respect. It is open, flat, and not especially mysterious. The directions can line up everywhere because the surface does not bend back on itself in a way that creates a global conflict. A sphere is another matter. The moment you try to carry one smooth, directional arrangement all the way around, you discover that every neat patch you create has consequences elsewhere. Brush downward from the top, and the hairs line up nicely for a while. Continue toward the side, and still things seem reasonable. Move further, and now the directions begin to curve around the body of the sphere. Keep going, and eventually you arrive at a region where the pattern no longer knows what to do. The directions are being pulled into incompatible requirements by the shape itself. Somewhere a swirl appears, or a tuft, or a point where the hair simply cannot be assigned a clean non-zero direction. That word non-zero matters, even if we are avoiding formulas and technical symbols. In this context, it means that the hair should genuinely point somewhere along the surface, not vanish, not collapse into a point where the assigned direction is effectively nothing at all. The theorem says you cannot avoid at least one such failure point on a sphere if you insist on smoothness everywhere else. There must be a place where the directional field gives out. It helps to notice that the problem does not lie in motion, force, or effort. It is not that combing is difficult because you lack skill or because the sphere is slippery. It is not a matter of dynamics. It is a matter of possibility. Even an infinitely patient comb in the hands of a mathematically enlightened barber cannot do what the theorem forbids. That is why the statement has such force. It is not saying that complete grooming is hard. It is saying that complete grooming is impossible in principle. There is something satisfying about impossibility results when they are honest enough to look absurd at first. A silly name often hides a serious border in mathematics. Once you understand the border, the silliness becomes a kind of camouflage that lets the insight travel further. People remember the hairy ball theorem because the image is ridiculous. They respect it because the image happens to encode a precise and non-trivial fact, and they keep returning to it because the theorem gives a clean example of how shape alone can force a limitation on what patterns are allowed. Now, if the morning mirror is our starting point, the next step is to separate the human idea of tidy hair from the mathematical idea of a smooth direction. These are related, but they are not identical. Real grooming cares about appearance, density, length, texture, and whether one can leave the house without looking as though one has argued with a thunderstorm. Mathematics strips all that away. It cares only that at every point on the surface, there is a direction tangent to the surface and that these directions vary continuously from point to point. No sudden jumps, no places where the pattern snaps from one orientation to another without warning. The continuity is essential, because otherwise the problem would be trivial. You could simply assign directions carelessly and ignore the resulting chaos. The challenge is to create a smooth field, something coherent and unbroken. This smoothness requirement is what makes the failure points meaningful. They are not artifacts of bad planning. They are the unavoidable places where smooth global order cannot be maintained. In everyday language, we might say the hare has to misbehave somewhere. In mathematical language, the vector field must vanish somewhere. These are two descriptions of the same underlying fact, one dressed for a living room and one dressed for a seminar room. The everyday description remains useful though, because it reminds us that the theorem is fundamentally visual. You can almost see the obstruction before you can explain it. Try a few mental experiments. Suppose you begin at the north end of the sphere and brush every nearby hair southward. That seems straightforward. The hairs radiate away from the top. As you continue downward across the sphere, the arrangement stays smooth for a while. But now ask what happens near the south end. All those smooth southward directions are converging there. What does the hair do at the very bottom? Which way is south once you have reached the southernmost point? There is no further direction along the surface to continue in the same way. The pattern collapses into a singular point. So perhaps you try a different strategy. Instead of brushing from one pole to another, maybe you circle around the sphere, making the hairs run along lines of latitude. This avoids the problem at the poles, perhaps, except it does not. Near the poles, those circular paths shrink. At the very top and bottom, there is no clean horizontal circle left to follow. The arrangement still breaks down. You have not removed the obstruction. You have only moved it into another costume. This migration of the problem is worth dwelling on because it teaches a useful habit of mind. In mathematics, when every proposed workaround relocates the difficulty rather than eliminating it, that is often a sign you are dealing with a structural obstruction. The obstruction is not tied to one method. It belongs to the object itself. Different strategies reveal it in different places, but they do not dissolve it. The stubborn point is not a flaw in the approach. It is a message from the surface, and the message is simple enough. A sphere does not support an everywhere non-zero smooth tangent direction field. That is the clean version, but the hairy image remains more memorable because it captures the emotional texture of the discovery. You keep trying to smooth the thing. The thing keeps refusing in one spot or another. The refusal is not dramatic. It is not explosive. It is quiet, inevitable, and slightly irritating in exactly the way a true theorem ought to be when it first takes hold. There is also a subtle pleasure in how democratic the theorem feels. You do not need advanced machinery to appreciate its content. You can explain the statement to a child, an engineer, a meteorologist, a philosopher, or someone who has simply wrestled with an uncooperative fringe before breakfast. Each person will understand a version of the difficulty. What changes with expertise is not whether the problem is intelligible, but how deeply one can see into the reason behind it. For someone coming from geometry, the reason lies in the structure of the sphere as a closed, even-dimensional surface. For someone coming from topology, the theorem sits naturally among broader facts about vector fields and the invariance of manifolds. For someone coming from physics, it connects to flows and orientations on curved spaces. For someone coming from ordinary life, it remains a perfectly good reason to look suspiciously at a tennis ball and imagine it with fur. That range is part of the theorem's charm. It belongs to serious mathematics, yet it never entirely loses its comic edge. In fact, the comic edge helps. It prevents the idea from floating off into sterile abstraction. It keeps the mathematics attached to touch and sight and the stubborn reality of surfaces. Now, there is an easy mistake to make at this point, and it is useful to catch it early. One might think the theorem says that every hairy object has an unavoidable cowlick, but the statement is not about every object. Shape matters. A sphere has this property. Other surfaces behave differently. If the surface has a different topological character, the obstruction can disappear. That means the sphere is not merely an example, it is a specific kind of example. The impossibility comes from what the sphere is. This will become especially important later, because one of the most revealing comparisons in all of topology is between the sphere and the torus, the surface shaped like a donut. The torus can support a smooth, non-zero tangent direction field everywhere. You can, in the hairy metaphor, comb a hairy donut flat. There is no theorem of inevitable cowlicks for the donut. That contrast tells us immediately that the issue is not hairiness in general, nor curvature in some vague everyday sense, but a deeper property of the surface. But for now, it is enough to sense that the sphere is special in its resistance. It looks innocent because it is so symmetrical. In fact, perhaps because it is so symmetrical, the sphere has no preferred direction built into it, no natural eastward grain, no distinguished flow line that can guide every local choice. Every point is locally similar to every other point, and yet the global arrangement is constrained. That combination of local sameness and global obstruction is exactly the sort of thing topology loves to study. And yes, topology is beginning to approach, even if it has not yet properly introduced itself. It is the branch of mathematics that asks what remains unchanged when shapes are stretched or bent without tearing or gluing. It cares less about exact measurements than about connectedness, holes, and the deep structure of surfaces. It is the natural home for the hairy ball theorem because the theorem is not really about metric detail. You do not need a perfectly round sphere of precisely known radius. The relevant truth survives smooth deformation. Inflate the sphere a little, squash it slightly, make it more like a lumpy orange than a perfect globe, and the obstruction remains. The hair still refuses full compliance. That point is surprisingly important. It means the theorem is robust. It is not a trick of exact symmetry. The impossibility is not balanced on a knife edge of ideal conditions. It belongs to the whole family of sphere-like surfaces. The world can be imperfect and the theorem still holds. In that way, it resembles many good scientific insights. The exact details may vary, but the structural fact persists. And perhaps that is why the morning struggle is such a fitting image after all. Real life rarely presents us with exact ideal forms. We work with approximations. Faces are not symmetrical, weather is not still, routines are not clean, and yet patterns emerge. Mathematics often begins by idealizing, but its strongest ideas are the ones that continue to say something even after the perfection has been relaxed. The hairy ball theorem survives that relaxation. It is not defeated by small lumps and asymmetries. The basic obstruction stays put. So when we imagine brushing the sphere and watching the stubborn tuft migrate from place to place, we are not just enjoying a quaint metaphor. We are meeting a genuine boundary between what local smoothness can achieve and what global structure permits. The tiny domestic annoyance of an uncooperative patch becomes, in mathematical form, a lesson about the limits imposed by shape. That is a rather good return on something as ordinary as a comb. It also sets up an important question. If the sphere cannot be fully combed, how exactly does mathematics decide that? What kind of reasoning lets us move from a visual irritation to a rigorous impossibility? The answer does not begin with hair at all. It begins with a shift in attention. Instead of asking how a surface looks, mathematics asks what a surface is, in the deeper sense of how it is put together and what kinds of continuous patterns it can support. Once that shift happens, a hairy ball stops being a joke object and becomes a surface carrying directional information. And from there, topology begins to do what it does best, which is to notice that appearances are often the least important thing about a shape. That is where topology quietly steps in, not with a ruler or a protractor, but with a very different set of priorities. If ordinary geometry is the part of mathematics that asks how long something is, how sharply it bends, or what angle it makes, topology is the part that asks a stranger question. It asks what remains true when those details stop mattering. It asks what a shape is when you stop judging it by exact appearance and start paying attention to its deeper structure. This can sound a little elusive at first, but the basic instinct is simpler than the word makes it seem. Topology studies properties of shapes that survive stretching, squashing, and bending, so long as you do not tear the shape, glue separate parts together, or punch new holes through it. If you like, it is the mathematics of continuity. A topologist is not terribly worried about whether a circle is drawn neatly, whether a sphere is perfectly round, or whether a surface has been dented by a rough morning. What matters is the way the surface hangs together. That difference in emphasis is exactly what the hairy ball theorem needs, because the theorem is not really about neatness in the everyday sense. It is not about whether the hairs are pretty or symmetrical or brushed with sufficient discipline. It is about whether a certain kind of smooth directional pattern can exist on a surface at all. And to answer that question, you need a branch of mathematics that is willing to ignore the cosmetic details and focus on the underlying shape. The eye is not always helpful here. The eye likes appearance. It notices roundness, sharpness, smooth polish, symmetry, and size. It notices the difference between a beach ball and a bowling ball, between a perfect orange and a slightly battered one, between a coffee mug and a donut, and it assumes these visible differences must be mathematically decisive. Sometimes they are. But topology has a way of looking past those first impressions. It asks, if I were allowed to deform one object continuously, without cutting or attaching, could I turn it into the other? If the answer is yes, then from the topological point of view they are the same sort of shape. That is the part that tends to make people either smile or become briefly suspicious of mathematics. You're told that a coffee mug and a donut are topologically alike, and understandably you wonder whether mathematics has finally become too comfortable with itself. But the point is not that mugs and donuts are visually identical or practically interchangeable, which would make breakfast rather confusing. The point is that each has one hole. If you imagine both objects made of perfectly flexible rubber, you can gradually reshape one into the other without tearing the material or sealing the hole. The handle of the mug becomes the hole of the donut. The rest is just patient deformation. This is not a party trick, it is a clue. It tells you that topology sees something deeper than appearance. It sees connectedness, boundaries, holes, and the global layout of a shape. It is much less impressed by exact measurements than our eyes are. Two things that look dramatically different can be topologically alike, while two things that look almost identical can turn out to differ in an important structural way. Now, that way of seeing is particularly useful when you're dealing with surfaces that carry directions, because the problem of assigning directions smoothly is not controlled by exact size or local curvature alone. What matters is the overall topological character of the surface. A perfect sphere and a slightly lumpy sphere share the same essential obstruction. You still cannot comb either one flat everywhere. The difficulty is not hiding in the precision of the roundness. It is built into the kind of surface you are dealing with. This is one of the reasons topology can feel so powerful once you get used to it. It can take a problem that looks geometric or physical and say, actually, the answer does not depend on those finer details. The answer is already determined by the broad structure of the space. In the case of the hairy ball theorem, that means the theorem is not really about ideal polished globes. It is about any smooth surface that has the topological character of a sphere. Squash it a bit, stretch it gently, make it potato-like if you must, and the same fundamental problem survives. Somewhere the directional field has to fail. If you are the sort of person who likes the idea that the universe contains hidden rules, this is a very satisfying moment. It means the obstruction is not fragile. It is not an accident of perfect symmetry. It is a robust fact about the structure of the surface. You cannot escape it by making the sphere slightly uglier in a way that is reassuring. Mathematics is often at its most convincing when its truths do not vanish the moment reality becomes a little untidy. Let us make the idea more concrete. Suppose you have a rubber sheet laid out flat. You can mark a small arrow at every point, all pointing in the same direction, and the sheet is perfectly content with this. The arrows vary smoothly because they do not vary at all. Every point agrees. Nothing dramatic happens. Now roll that sheet into a cylinder, like a label wrapped around a can. You can still arrange arrows smoothly all around the cylinder without trouble. The shape has changed, but not in a way that introduces the kind of obstruction the theorem cares about. But if you take a sphere, the same plan fails. Not because a sphere is curved in the everyday visual sense, though it is, but because it is a closed surface of a certain topological type. It has no edge. It encloses a volume. It is simply connected in a specific technical sense. Most importantly for our purposes, it belongs to a family of shapes that do not admit an everywhere non-zero smooth tangent direction field. That statement sounds much drier than the hairy version, but it is the same truth wearing formal shoes. Topology helps because it teaches you to look away from the exact picture and ask a more structural question. What sort of surface is this? What are its global constraints? What continuous arrangements can it support? Once you have learned to ask that, the hairy ball theorem stops seeming like a weird statement about grooming and starts looking like a natural consequence of a broader topological reality. There is another useful habit topology encourages, and that is skepticism about local evidence. A small patch of a sphere can fool you. It looks flat enough. You can comb a little neighbourhood of points in a perfectly smooth direction and feel quite pleased with yourself. The trouble is that local success proves very little about global possibility. Topology has a long memory. It remembers the whole surface even when you are staring at a tiny piece. This is not only a mathematical lesson, it is a general lesson in how complex things behave. Local order does not guarantee global compatibility. Small regions can each make sense on their own and still fail to fit together into a coherent whole. You can feel this in city planning, in computer code, in filing systems, in committee decisions, and occasionally in family holidays. Every local choice seems reasonable, then the overall structure rebels. Mathematics gives that tension a very clean form. The sphere lets you behave nicely in every little neighbourhood. It only objects when you try to extend that niceness everywhere at once. That is exactly the kind of situation topology was born to understand. It is a field with a remarkable talent for identifying when a global obstruction is hiding behind local simplicity. It looks for the things that cannot be fixed by working harder in one corner. It asks whether the difficulty is structural rather than procedural. If the problem is structural, then no amount of local ingenuity will remove it. You need to understand the whole space. This is why topology often feels a little philosophical without ever needing to become vague. It is interested in identity beneath distortion. It asks when two shapes are fundamentally the same and when they are not. It wants to know what features survive continuous change. A topologist can watch a surface stretch like warm dough and still say with confidence which truths remain untouched. To see what that means in practice, imagine a sphere made of soft rubber. You squeeze it gently into an oval. Nothing topological changes. You press one side inward and let the other bulge. Still the same topological kind of object. You could make it resemble a misshapen fruit, or the sort of stress ball that has had a difficult office life. As long as you do not tear it or create a hole, the topological nature stays the same, and with it, the hairy ball obstruction stays the same. Now imagine instead that you punch a hole right through the shape and turn it into something ring-like. That changes everything. Not visually everything, perhaps, but topologically everything that matters. You have altered the connected structure of the surface. You have changed the answer to questions about what kinds of continuous fields the surface can support. In topology, a hole is not a decorative detail, it is a deep fact. This is why the famous mug and donut comparison matters. It is not cute because it is surprising. It is useful because it teaches you what topology considers essential. A handle and a central hole count for more than exact shape. The presence or absence of that hole changes what kinds of global patterns the surface can support. Later on, when we compare the sphere to the donut more carefully, that difference will explain why one can be combed flat and the other can be combed happily all day without producing an unavoidable cowlick. For the moment, the important thing is to see that topology is giving us new eyes, or perhaps not new eyes, but a way of seeing when the ordinary visual impression has stopped being reliable. The eye says this object is almost round, so perhaps it behaves almost like every other roundish object. Topology says, tell me whether it has a hole, tell me whether it has an edge, tell me how it is connected. Then we can begin talking about what is really possible on it. That shift can feel strange because human perception is deeply loyal to metric detail. We naturally care how big something is, whether it is straight, whether it is sharply bent, whether two things look alike. Topology asks you to relax that instinct and notice something else. It is a bit like listening to a melody played on different instruments. The timbre changes, the volume changes, the texture changes, but the underlying tune can remain the same. Topology listens for the tune of a shape, and once you start listening for that tune, a great many problems sound different. Suddenly you see why exact curvature is not the heart of the hairy ball theorem. A perfect sphere and a slightly squashed sphere may differ geometrically, but topologically they are singing the same tune. The obstruction to smooth combing belongs to that tune, not to the polish of the performance. There is a further reason topology is the right language here. The theorem is about continuity. It is about assigning a direction at each point and demanding that the assignment vary smoothly across the surface. Continuity is one of topology's most natural concerns. It studies what happens under continuous deformation, what maps can be made continuous, what structures can be extended without tearing or jumping. If geometry asks for precision, topology asks for coherence. That word coherence matters. When you brush the hairs on a sphere, you're trying to impose a coherent global direction field. Each tiny hair is a local instruction. Taken together, they are a global pattern. The question is whether the surface allows such coherence without a failure point. Topology answers by looking not at the individual hairs, but at the structure of the surface they live on. In effect, it says, before worrying about the details of the field, understand the stage on which the field must perform. This stage and performance way of thinking is often very helpful. A play can fail because the actors are confused, but it can also fail because the stage itself makes the script impossible. The hairy ball theorem is a stage problem. No matter how clever the directions are, the sphere does not allow the performance to be completed without at least one moment of breakdown. There is something pleasingly strict about that. Mathematics is sometimes at its gentlest when it is most uncompromising. It does not scold. It simply says, here is the limit. On this kind of surface, this kind of arrangement cannot exist. And because the statement is topological, it applies broadly. Not only to the ideal classroom sphere, but to the whole family of sphere-like surfaces. You can see echoes of this topological viewpoint in many places outside pure mathematics. When meteorologists study wind patterns on Earth, they are dealing with a directional field on a roughly spherical surface. When computer graphics designers try to lay directional textures over curved models, they run into related issues about singular points and continuity. When physicists study certain kinds of fields on curved spaces, they meet topological constraints that do not care about exact metrics so much as global structure. In each case, topology is there in the background, quietly insisting that the surface itself has a vote. It is worth noticing that topology often works by making impossibility elegant. Instead of forcing a construction, it reveals the reason no construction can succeed. This is one of its great strengths. There is a certain relief in learning that some obstacles are not due to personal failure, poor technique, or insufficient cleverness. They are built into the situation. The right response is not frustration, but understanding. If that sounds suspiciously like life advice sneaking in through the mathematics, I promise the theorem did not ask for that burden. Still, it is hard not to notice the parallel. Some arrangements fail because we have done them badly. Others fail because the structure never permitted a perfect version to begin with. The value of topology is that it helps distinguish one kind from the other. So when the eye looks away from exact shape, What topology sees is not less reality but a deeper layer of it. It sees the features that survive distortion. It sees which surfaces are fundamentally alike and which differ in decisive ways. It sees that a local patch of good behaviour proves very little about the whole. And it sees, in the case of the sphere, that the dream of a perfectly combed directional field is not merely difficult. It is ruled out by the kind of surface the sphere is. That is the broad topological picture. But to make it feel fully solid, we need to come back down from the grand view and look more carefully at the surface itself. Because once topology has taught us to ignore the wrong details, the next step is to understand the right ones. What exactly counts as a surface here? What does it mean for a direction to lie smoothly along it? Why does the sphere allow order in tiny neighbourhoods but refuse it globally? Those questions bring us to the practical heart of the matter, where the language of surfaces and smoothness begins to matter in a very concrete way. The word surface sounds so harmless that it almost slips past without inspection. We use it all the time. The surface of the table, the surface of the water, the surface of the earth. It sounds like the outside layer of a thing, the part you touch, the part you see, the part that meets the air and gets the blame for whatever lies underneath. But in mathematics, a surface is not just the outer skin of an object in the everyday sense. It is a place in its own right, a world with rules, directions, neighbourhoods, and a certain amount of quiet personality. And if you want to understand why a hairy ball cannot be combed flat, you need to understand what sort of world a surface really is when mathematics begins to pay attention to it carefully. The first useful fact is that a surface can be curved overall while still looking flat up close. This is one of those statements that is both obvious and surprisingly deep. Anyone who has looked at the horizon from the ground knows the Earth does not feel curved beneath their shoes. A small patch of a globe behaves much like a flat sheet. A tiny region on a sphere can be treated for many purposes as if it were just a little plane. That local flatness is what makes the hairy ball theorem interesting rather than trivial. If every part of the sphere looked obviously twisted and unruly, even in a tiny patch, then there would be no surprise in the theorem at all. But every small neighbourhood behaves politely. The trouble only shows up when you try to connect all those neighbourhoods into one smooth arrangement across the entire surface. That is the first tension worth holding on to. Locally manageable does not mean globally possible. A sphere lets you forget it is a sphere when you look too closely. It lets you comb a tiny patch quite happily. In fact, it lets you comb many tiny patches quite happily. What it does not let you do is make all of those local grooming decisions fit together without conflict everywhere at once. Now, what does it mean to comb hair on a surface in the mathematical sense? It means that at each point on the surface you want to choose a direction that lies along the surface rather than sticking out of it. If you imagine a little ant standing on the sphere, the direction you assign should tell the ant which way to walk while staying on the surface. It should not tell the ant to launch into the air or burrow inward. The direction must lie in the local surface itself. That idea is so central that mathematics has a name for it, but the image is enough. The assigned direction has to skim the surface, not leave it. This becomes slightly more subtle than it first appears, because on a curved surface there is no single universal notion of straight across. On a flat table, you can point all the arrows east and be done with it. Every point understands what east means in the same ordinary way. But on a sphere, what counts as a given direction depends on where you're standing. The surface is curving under you all the time. A direction that makes perfect sense near one point cannot simply be copied wholesale to a distant point without being interpreted relative to the local surface there. That is why the little ant picture matters. Each point on the sphere has its own small flat world, its own local sense of what counts as along the surface. To assign a smooth field of directions, you have to make a choice in each of those little worlds, and you have to make the choices fit together continuously as you move from one point to the next. The sphere is not objecting to the existence of directions at individual points. It is objecting to the dream of making all those local choices line up into one global pattern, without any place of collapse. Smoothness is the next ingredient, and it is doing more work here than its calm appearance suggests. In ordinary speech, smoothness often means pleasant texture, no bumps, no roughness, the opposite of scratchy or jagged. In mathematics, when we speak about a smooth directional field on a surface, we mean that the direction changes gently from point to point. No sudden flips, no abrupt jumps, no place where the pattern behaves as though it changed its mind between one breath and the next. If you move along the surface, the assigned direction should vary in a continuous way. That requirement is not decorative. Without it, the problem becomes far less meaningful. You could assign directions in a chaotic patchwork fashion and declare victory simply because every point had been given something. But that would not reflect any genuine coherence in the surface. It would be like claiming you have organised a library because every book has been thrown somewhere inside the building. The point of smoothness is that the arrangement should make sense as a whole. Nearby points should not disagree violently. The field should feel like one pattern rather than many unrelated local decisions. This is where the trouble begins to sharpen. Small patches of a sphere do not mind smoothness. On a tiny patch, you can make all the arrows run in roughly the same direction, and everything behaves beautifully. The field is smooth, the hairs lie down nicely, the ant knows where to walk. The difficulty emerges only when you try to continue that gentle pattern farther and farther, wrapping around the surface and demanding that no point be left without a clean direction. One way to feel the issue is to think again about starting near the top of the sphere. Suppose you choose directions that all point away from that top point, like lines spreading outward from a cap. Near the top, this seems perfectly sensible. Every nearby point has a direction along the surface. The pattern varies smoothly. If you move a little, the arrows change gently. Nothing alarming appears. Continue farther down and the pattern still seems well behaved. The directions keep spreading outward. But now ask what happens exactly at the top itself. Every surrounding point points away from it, but at the top there is no single preferred direction that matches them all smoothly. The pattern breaks. The centre of the spread is a singular place, a point where the directional field cannot be defined in the same smooth, non-zero way as elsewhere. So perhaps you try to avoid that by choosing a different arrangement. You make the directions run around the sphere in horizontal loops, like latitude lines on a globe. Again, over most of the sphere this works nicely. Every point away from the top and bottom can follow a circular path. The field is smooth, the hairs seem obedient. But as you approach the very top or bottom, those circles shrink. At the poles, the horizontal loop has collapsed to a point. There is no non-zero direction there that continues the pattern smoothly. The singularity reappears. This is an important lesson. The problem is not that one particular brushing strategy fails. The problem is that every smooth strategy fails somewhere. Some arrangements hide the failure at the top and bottom. Others hide it in a swirl. Others distribute the trouble in more complicated ways, but none remove it entirely. Smoothness does not rescue you. It makes the obstruction visible. That phrase visible is perhaps slightly misleading, because often the obstruction becomes most visible when you stop trusting the eye in the ordinary way. The eye likes to judge by appearance. A nearly combed sphere looks almost solved. A field that is smooth everywhere except one tiny place can seem as though it ought to be repairable with a little extra care. Mathematics says otherwise. That tiny place is not a cosmetic flaw. It is the structural debt the sphere always demands. Another useful way to think about smoothness is to imagine walking along the surface while watching the assigned direction at your feet. On a smooth field, the direction should turn gradually, never snapping abruptly. If the surface were flat and endless, you could simply keep the direction fixed and nothing would go wrong. On a curved, closed surface like the sphere, the direction must gradually adapt as you move, because what counts as along the surface keeps changing with position. The deeper issue is that when you travel far enough, the cumulative effect of those local adaptations cannot be made globally consistent without some point where the field vanishes or becomes undefined. That sentence is close to the heart of the matter. Smoothness is a local condition. The obstruction is global. The field can behave beautifully in every tiny neighbourhood and still fail to exist everywhere at once. This contrast between local possibility and global impossibility is one of the things that makes the hairy ball theorem feel both intuitive and surprising. Intuitive because each local patch behaves exactly as you would hope. Surprising because the whole surface still refuses the full construction. You can find analogies for this outside mathematics, though none are perfect. Think of trying to lay flat wrapping paper smoothly over a round object. Any small region goes down without complaint, but the larger the area you try to cover, the more wrinkles or folds begin to appear unless the material can stretch. The local patch does not warn you about the global strain that is coming. Or think of sewing a garment from pieces that each fit nicely on their own, but start to pull awkwardly when assembled into a complete whole. The problem is not in any one seam viewed in isolation. It emerges from the way the entire structure has to fit together. With surfaces, this becomes especially important because the geometry under your feet is always changing from point to point. A flat plane has a kind of directional generosity. Once you pick a direction, the entire plane is willing to honour it. A sphere is less permissive. Every point has its own local tangent world, and although each of those worlds looks flat in isolation, the collection of all of them around the sphere carries a subtle twist that prevents one smooth, non-zero field from existing globally. You do not need the machinery of advanced mathematics to sense this, but the machinery exists because the sensation alone is not enough. The sphere is not merely inconvenient, it has a provable obstruction. And the language of surfaces and smooth fields is the bridge between the picture and the proof. The more carefully you define what a surface is, what it means for a direction to lie along it, and what it means for those directions to vary smoothly, the more clearly the theorem becomes a statement about structure rather than a piece of visual folklore. There's another point worth noticing here. When we say the sphere has trouble with smoothness, we do not mean the surface itself is rough. The sphere is as smooth a surface as one could wish for in the ordinary geometric sense. The trouble lies not in the texture of the sphere, but in the smoothness of the directional field we are trying to place on it. The surface is blamelessly elegant. It is the global organisation of directions that runs into difficulty. This matters because it shows the obstruction is not caused by defects or corners or sharp edges. It comes from the closed curved nature of the surface itself. That makes the theorem a very clean result. It is not a story about irregularity spoiling a good plan. It is a story about perfection still being unable to support a certain kind of order. Even the ideal sphere cannot do it. In a curious way, the sphere is too complete. Because it closes in on itself and offers no boundary, every directional choice eventually has to answer to every other one. There is nowhere for inconsistency to hide off stage. Boundaries, in fact, are often what save you in problems like this. If a surface has an edge, you can sometimes push the trouble to the boundary and leave the interior well behaved. A sphere offers no such escape route. It is all interior in the sense that there is no edge to deposit the awkwardness. The failure point must live on the surface itself. This helps explain why the theorem feels so tied to the idea of a world rather than a patch. A sphere is a complete arena. It is a closed universe for the directional field. The field must account for the whole thing. There is no external frame to lean against, no outside direction that all points can reference consistently while staying tangent to the surface. The sphere insists on internal coherence, and that insistence is what makes the obstruction unavoidable. It is also worth being clear about what the theorem does not say. It does not say that you cannot assign directions on most of the sphere. You can. It does not say you cannot make the field smooth wherever it is defined. You can. It does not even say the bad points have to look the same in every arrangement. They do not. Some patterns may have one singular point. Others may have several. Some may produce swirls. Others may produce saddle-like behaviour. The The theorem only says that you cannot get rid of all such points at once. At least one must remain. That small phrase, at least one, has a nice mathematical flavour to it. It leaves room for many patterns while still drawing a sharp line. Mathematics often works this way. It does not prescribe one unique picture when many are possible. It identifies the boundary that all possible pictures must respect. You may distribute the trouble however you like, but the total cannot be reduced to zero. If you are listening with half a mind on weather, this is the point where the theorem begins to sound surprisingly physical. Wind on the Earth is a directional field along a roughly spherical surface. If the wind varies smoothly, then somewhere there must be a point where the horizontal wind speed is zero. A calm point is not merely a meteorological accident, it is something the sphere itself quietly requires. Again, exact real-world weather is more complicated, but the topological core survives. The theorem is telling you that certain patterns of flow on surfaces are constrained by the shape of the world they inhabit. That is a lovely thing for mathematics to reveal. It takes a problem that begins with imaginary fur and ends by saying something about atmospheric motion on a planet. It reminds you that surfaces are not passive backdrops. They participate in what can happen on them, and once you begin to think of surfaces this way, as active constraints rather than neutral stages, many other questions open up. Why does the sphere force singularities while some other surfaces do not? What is the exact feature of the sphere that creates the obstruction? How can local flatness coexist with global impossibility so peacefully? These are not separate questions. They are all ways of asking what the sphere is really doing behind the scenes, when it politely allows every small patch to behave and then refuses the full arrangement anyway. The answer, at least in spirit, is that the sphere carries a kind of topological bookkeeping. Every attempt to place a smooth tangent field on it accumulates a certain amount of directional turning, and the total cannot balance out without singularities. The exact formal language can wait. The important thing for now is the idea that smoothness alone does not guarantee success. Smoothness must live inside the wider architecture of the surface. On the sphere, that architecture imposes a cost, and that cost is precisely what makes the next step so satisfying. Once you understand that the problem is not roughness, not poor grooming, and not local geometry in isolation, you are ready to face the central claim directly. Not just that the sphere is awkward, but that every sphere must keep one unruly spot, one unavoidable place where perfect alignment gives way, and the surface quietly reminds you that global order has limits. That claim sounds almost too neat when stated plainly, but it is exactly the point. A sphere does not merely tend to produce a troublesome spot, it must produce one. Somewhere on the surface, no matter how cleverly you arrange the directions, there has to be a place where the pattern breaks down. In the language of the image, every sphere must keep one cowlick. Now, that does not mean there is only ever one such point. A sphere can have several awkward places. You could arrange the hair so that 2 swirls appear, or 4, or some more elaborate collection of trouble spots. The theorem is not telling you that nature or mathematics insists on a single lonely tuft sitting at the top like a badly planned haircut. What it says is that you cannot have none. Total obedience is forbidden. Perfect, all-over smoothness without any singular point is not available on a sphere. To see why this is true, it helps to return to the difference between local order and global order, because that difference is doing nearly all of the important work. If you zoom in close enough on any part of the sphere, the surface looks almost flat. In that tiny neighbourhood, you can point the hairs in a nice smooth direction, and everything seems fine. The trouble appears only when you try to extend that neat local choice farther and farther, without ever losing continuity. The sphere lets you succeed in every small place. It defeats you only when you try to succeed everywhere at once. That fact alone tells you something useful. The obstruction is not a local flaw. There is no tiny patch on the sphere that is inherently impossible all by itself. Every little patch behaves. So the reason for the breakdown must live in the large-scale structure of the surface. It has to come from the way the whole sphere closes around itself and asks every local arrangement to fit into one worldwide pattern. One of the best ways to feel this is to imagine trying several different strategies and noticing that each one fails in its own way. Suppose you begin at the very top of the sphere and brush all the hairs outward, away from that top point. Around most of the surface, this produces a perfectly respectable pattern. The hairs spread smoothly, nearby points agree with one another, nothing abrupt happens. But the top point itself has a problem. Every direction nearby is pointing away from it, yet at the top there is no single sideways direction that continues the pattern. The top becomes a singular point. The cowlick is concentrated there. So then you try the opposite idea. Instead of brushing away from a top point, you brush the hairs in horizontal loops around the sphere. Now the top is not the source of a radial spread, which seems promising. The hairs circle around nicely over much of the surface, but as you move toward the very top or bottom, those loops shrink away. At the poles, there is no non-zero circular direction left to assign. The problem has not vanished. It has simply moved. This is already enough to suggest a deeper rule. The singularity is not tied to one specific pattern. The sphere itself is demanding that any smooth pattern leave behind at least one unresolved place. The trouble can migrate, split, combine, or hide in more complicated arrangements, but it cannot be eliminated. There is an important idea buried in that sentence, and once you notice it, the theorem becomes much easier to trust. The sphere does not care about your particular choice of combing. It cares about the total topological burden carried by the pattern. Each singular point contributes something to that burden, and on a sphere the total cannot come out to zero. That is the deeper reason every sphere must keep at least one cowlick. Now that word burden is only a metaphor, but it points toward a real mathematical concept. Around a singular point, the surrounding directions twist or turn in a certain way. If you walk in a little loop around the singularity and watch how the hairs are oriented, you find that the direction rotates as you go. In some singularities, the pattern turns in a way that feels like a source or a sink, with directions spreading out or flowing in. In others, it turns more like a saddle, with some directions approaching and others leaving. These different behaviors are not all equivalent. They carry different local signatures. The remarkable part is that when you add up those local signatures over the whole sphere, the total is fixed by the shape of the surface. You're free to choose different patterns. You're free to move the singularities around. You're even free to trade one kind of singularity for several others, provided the bookkeeping still balances. But you're not free to make the total disappear. The sphere insists on a non-zero total, and that means some singularity must remain. This is why the theorem is stronger than a visual hunch. It is not just that spheres look awkward to comb. It is that there is a topological accounting system underneath the picture, and the numbers never let you settle the debt completely. A perfectly smooth non-zero field everywhere would mean no singularities at all, which would make the total come out wrong for a sphere. Since the total is fixed by the surface, the absence of singularities is impossible. You can think of it like trying to flatten a wrinkle in a fitted sheet. You may succeed in one corner, but then another corner gathers tension. Smooth that one, and the wrinkle migrates somewhere else. If the sheet were really just lying open on a bed, perhaps eventually you could pull enough fabric around to settle it. But the sphere is not an open sheet. It is closed. There is no spare edge to tug on, no extra margin where the strain can be released. The tension has to live somewhere on the surface itself. That is the everyday version. The mathematical version is stricter. It says that the unavoidable bad spots are not mere practical annoyances. They are singularities forced by the topology of the sphere. Every attempt to define a smooth tangent direction field everywhere runs into them. because the global turning behaviour around those points has to add up in a way determined by the surface. There is a beautiful economy in that. A sphere may look simple, but it carries enough global structure to impose a universal rule on all smooth direction fields placed upon it. That is one of the reasons topology often feels slightly magical, even when the reasoning is rigorous. A large-scale property of a shape dictates what every possible local arrangement must eventually do. At this point, it is worth clearing up a subtle misunderstanding that often slips in. When people first hear the hairy ball statement, they sometimes imagine that the obstruction is caused by the curvature of the sphere in the ordinary geometric sense. After all, a sphere is curved, so perhaps the curving is what makes the hair misbehave. But that idea is only partly right, and if taken too literally, it becomes misleading. The crucial issue is not curvature alone, as geometry usually measures it. The crucial issue is the topological kind of the surface. There are surfaces that are curved, and yet do not suffer this same obstruction. A torus, the donut-shaped surface, can carry a smooth non-zero tangent field everywhere. You can comb the hairs around the ring and never be forced into a singular point. So if curvature alone were the villain, that would not be possible. The real difference is deeper. The sphere and the torus are not the same kind of surface topologically. The sphere has no hole. The torus has one. That difference changes the global bookkeeping completely. This is an excellent reminder that the cowlick is not a curse attached to roundish things in general. It is a structural feature of the sphere and sphere-like surfaces. The theorem belongs to a family of ideas in which the number and kind of unavoidable singularities are tied to deep invariance of the surface. Once you know that, the theorem begins to feel less like a novelty, and more like the first visible edge of a larger theory. Still, the hairy image remains the best guide, because it keeps the abstraction grounded. Picture the sphere once more, covered in tiny strands. Every local patch can be brushed. That much is easy. The challenge is not local grooming but global coherence. If you try to avoid one singularity, you create or preserve another. If you split one bad point into two milder ones, the total topological requirement is still there. The sphere does not care how you distribute the trouble, it only refuses to let the trouble vanish completely. There is a way of saying this that sounds slightly severe but is very helpful. On a sphere, perfection is not an available state for a smooth tangent field. You can have elegance. You can have symmetry. You can have almost everywhere order, but you cannot have total smooth non-zero alignment at every point. The theorem does not criticize your attempt. It tells you the attempt was aiming at something the surface does not permit. That makes the cowlick an honest feature rather than a defect. It is not evidence that the combing went wrong. It is evidence that the sphere is being true to its own topology. In ordinary life, we usually treat the stubborn tuft as the sign of a failed routine. In mathematics, the unavoidable singularity is part of the correct picture. If you produced a perfectly groomed sphere with no singular point at all, that would not be a triumph. It would be a contradiction. This turns the image upside down in a rather satisfying way. The cowlick is no longer the embarrassing leftover. It is the witness that the geometry has been understood properly. It is the place where the sphere tells the truth about itself. You can see why mathematicians like examples of this kind. They teach a general lesson very economically. Many global constraints do not announce themselves in each small neighbourhood. They emerge only when you try to impose one coherent structure over a whole space. And when they emerge, they often do so through singularities, boundary effects, or places where your pattern is forced to fail. The failure is not a flaw in the theorem, it is the theorem. This becomes even clearer if you imagine trying to remove the singularity by gradual adjustment. Suppose you notice a little whirl at one point and decide to smooth the hairs around it more carefully. The whirl might spread out and become less obvious, or it might drift across the surface, or it might split into multiple singularities of different types. But unless another singularity is present to interact with it in the right way, you cannot simply erase it. The topological bookkeeping forbids casual disappearance. The singularity is carrying some part of the total that the sphere requires. That word interaction matters because singularities can combine and cancel in more complicated settings, but only according to strict rules. Two trouble spots are not just two trouble spots. Their local turning behaviours matter. A source-like singularity and a saddle-like singularity do not contribute the same kind of local signature. In a larger pattern, some combinations can balance one another, others cannot. But on the sphere, the total still comes out to the same fixed value in the end, which means the field cannot be non-singular everywhere. Even without formal definitions, you can feel the force of that idea. It means the theorem is not about one lucky picture. It governs all pictures at once. Any smooth tangent field on a sphere must pay the same global tax, whatever local artistic choices it makes. This is one reason the theorem has such staying power. It teaches you what topology is really good at. Topology is not merely classifying shapes in an abstract cabinet. It is telling you what kinds of patterns, flows, and structures those shapes can support. It links the nature of the stage to the possibilities of the performance. On a sphere, the performance of an everywhere smooth, non-zero directional field is simply not in the script. There is also a quiet elegance in how minimal the theorem feels. It does not say the sphere is chaotic. It does not say most points must be bad. In fact, most of the sphere can look beautifully organized. The theorem asks for very little. It asks only that you accept at least one singular point somewhere. That is all. Yet that small, unavoidable exception changes the entire global story. One cowlick is enough to separate the possible from the impossible, and once you get used to that, you begin to notice similar patterns elsewhere. A tiny obstruction can encode a global truth. One point of failure can reveal the nature of an entire surface. The world of mathematics is full of these moments, where the smallest irregularity turns out to be the most informative feature. There is another practical reason to think in terms of cowlicks rather than only formal fields. Real phenomena often show singularities quite plainly. Swirls in fluid flow, calm points in wind patterns, defects in liquid crystals, orientation problems in texture mapping. All of these are places where some smooth directional organization fails or turns in a structurally significant way. The hairy ball picture gives you a very simple mental model for why such defects are not always removable. Sometimes the medium or surface itself requires them. That takes us naturally toward the Earth, because the planet gives the theorem one of its most memorable concrete lives. If you imagine the horizontal wind at every point on the Earth as a smooth tangent vector field, then the theorem says there must be at least one point where the horizontal wind is zero. Somewhere, at that moment, the air is still. The atmosphere may be busy elsewhere, but the spherical shape of the Earth forces the existence of calm. That is an extraordinary thing for a theorem with such a playful name to be able to say. Before we get there, though, it is worth appreciating what we have really learned here. Not just that a sphere keeps one cowlick, but why that sentence matters. It matters because it shows that singularities can be necessary. It matters because it separates local smoothness from global possibility. It matters because it introduces the topological idea that shapes carry invariant constraints on the fields they support. And it matters because the sphere, for all its simplicity, already contains enough structure to make perfection impossible in a very precise sense. Once you start thinking this way, the sphere begins to look less like a simple object and more like a quiet instructor. It allows order almost everywhere, but never everywhere. It permits elegant fields, but not flawless ones. It lets you smooth and smooth and smooth, and then calmly remind you that one small, unruly place must remain. Not as an accident, not as a punishment, but as a consequence of what the sphere is. And when that realization is firmly in place, the next question becomes hard to resist. Because if a theorem about imaginary hair can force a calm point on an entire planet, then the atmosphere itself becomes a very good place to watch topology stop being an amusing picture and start acting like a law of the world. Now the theorem stops being a charming little oddity about imaginary fur and starts brushing up against the actual planet under our feet. Because if you want a real-world example of a surface covered not in hairs but in directions, Earth is waiting patiently with an atmosphere full of them. At every point on the surface of the planet, the air is doing something. Sometimes it is racing along a coastline hard enough to rattle windows and turn umbrellas into doomed engineering experiments. Sometimes it's slipping quietly over fields with so little fuss that only a few leaves seem to notice. Sometimes it's rising, sometimes sinking, sometimes swirling around a pressure system in broad curves too large to see from the ground. But if we simplify a little, and only pay attention to the horizontal motion of the air along the surface, then we can imagine assigning a direction to each point on Earth. At this location, the wind is blowing northward. At that location, it is drifting westward. Somewhere else, it is circling around a storm. Taken together, those directions form a field over the surface of the planet. And now the hairy ball theorem quietly clears its throat. If the Earth is treated as a sphere, and if the horizontal wind varies smoothly enough from place to place, then there must be at least one point where the horizontal wind is zero. Not small, not weak, zero. Somewhere, at that instant, the air along the surface is still. That is one of those conclusions that sounds improbable right up until you see why the theorem has no reason to care about your initial doubt. The atmosphere may look busy almost everywhere. The weather map may be full of arrows, fronts, loops, pressure zones, and enough colour gradients to make the whole thing resemble abstract modern art. But topology is not interested in whether the map looks crowded. It is interested in whether the directional field can be smooth and non-zero everywhere on a sphere, and it cannot. So no matter how lively the winds seem across oceans, deserts, forests, mountain ranges, and the occasional city that insists on building all its streets in a way designed to accelerate drafts, somewhere there must be a calm point. That does not mean the weather must be boring there. It does not even mean the air above that point is doing absolutely nothing in every direction. The atmosphere is three-dimensional after all, and the theorem is about tangent directions along a surface. Air can rise or sink. Local conditions can be messy. The Earth is not a perfect mathematical sphere. Weather is not a perfectly smooth field. There are mountains, temperature contrasts, coastlines, turbulence, and more complexity than any sleepy evening narration should be asked to carry without a cup of tea. But even with those real-world qualifications, the theorem gives a striking conceptual truth. A smooth horizontal wind field on a sphere cannot be nowhere zero. Somewhere the planet must keep a calm spot. This is a wonderful example because it takes the theorem out of the realm of funny metaphors and lets it live in something familiar. We have all experienced wind. We know what it means to step from a sheltered street into an exposed open space and immediately regret our optimism about hair, hats, or any lightweight document not firmly attached to the hand. We know the sound of gusts in trees, the quiet push of air before rain, the strange confidence with which weather reports speak about masses of moving atmosphere as though they were slightly disorganized guests arriving from the west. Wind feels concrete. It feels physical. It feels very far from an abstract topological theorem with a name that sounds like it ought to be printed on novelty stationery. And yet here they are, meeting on the surface of the Earth. To see how natural that meeting really is, it helps to think about what a weather map is actually doing. A weather map is not merely showing pretty spirals for the sake of television graphics. It is representing a directional field spread over a curved surface. Every arrow on the map is a little local instruction. Air here is moving this way, air there is moving that way. The arrows vary across the globe, but ideally they do so continuously, at least on a large scale. One region feeds into another. The whole thing is a giant choreography of motion wrapped around a planet. And that choreography cannot be entirely free. The Earth itself imposes conditions. Some of them come from physics in the familiar sense. Uneven heating from the sun matters. Rotation matters. Pressure differences matter. The shape of continents matters. Mountains matter. Warm water, cold water, seasonal change, humidity, and the stubborn habit of the atmosphere to become dramatically complicated whenever human beings would prefer a simple forecast all matter. But beneath that layered physical story, there is also a topological fact. If you are assigning horizontal directions smoothly across something shaped like a sphere, at least one point of stillness has to appear. This is not the same thing as saying that every weather system is explained by the hairy ball theorem. Far from it. Topology is not replacing meteorology. It is placing a broad structural constraint underneath it. The theorem does not tell you where the calm point will be, how long it will last, or whether it will coincide with a region of high pressure, low pressure, or someone deciding not to trust the forecast and going out anyway in completely inappropriate shoes. It only tells you that the sphere does not permit the absence of such points altogether. There is a lovely modesty to that kind of result. Mathematics is not trying to control every detail. It is simply saying, whatever else happens, this much must be true. Of course, real winds do not just flow gently in tidy patterns waiting to be discussed by topology. They twist, curl, accelerate, stall, and reorganize themselves constantly. Around high and low pressure systems they spiral. Along the jet stream they race in long bands. Over mountains they are forced upward. Along coastlines they change character, depending on temperature contrast between land and sea. Near the ground they are slowed by friction and redirected by terrain. If you have ever watched trees move in one direction, while high clouds drift in another, you already know the atmosphere is not a single obedient sheet. It is layered, restless, and full of local complications. But none of this weakens the conceptual point. In fact, it makes it richer. Because once you realize that wind on Earth is one example of a directional field on a sphere, the atmosphere becomes a kind of moving illustration of the theorem. Swirls in the sky are no longer just weather. They are also evidence that smooth global organization on a sphere comes with unavoidable structure. The calm point is not an embarrassing exception to be ironed out. It is part of the truth of the system. One reason this example works so well is that it turns the theorem inside out. When people first hear about a hairy ball, they imagine trying to remove the bad spot. They imagine the cowlick as the problem. But with weather, the still point begins to seem almost natural. Of course, a global field of wind will have places where the motion settles or balances or turns around. Once you have seen enough weather maps, the idea of fixed flow everywhere starts to feel strangely implausible. The atmosphere is not a uniform conveyor belt. It is a living pattern of directional change on a curved world. The theorem tells you that stillness is not merely allowed within that pattern. In a smooth horizontal sense, it is required somewhere. This becomes even more interesting when you think about how storms and circulation cells organize themselves. A cyclone, for instance, gives you a region where the winds curl around a center. Depending on the hemisphere and the pressure pattern, the rotation changes direction, but the basic picture is familiar. Air does not simply march straight across the map forever. It curves, it wraps, it bends under the influence of rotation and pressure gradients. These swirling systems are full of directional structure, and that structure is easier to appreciate once you stop seeing the atmosphere as merely chaotic and start seeing it as a field spread over a surface with global constraints. Now, the theorem does not say every calm point must sit at the center of a storm, and it certainly does not say every swirl is the same thing as the unavoidable singularity in the pure mathematical picture. Real meteorology is much more detailed than that. Still, the broad analogy is deeply helpful. Around a singular point in a vector field, directions nearby often swirl or radiate in a distinctive way. Around weather systems, winds often do something similar. The geometry of the field becomes visible. You can see the atmosphere tracing out the kind of patterns mathematics describes more abstractly. There is also something unexpectedly grounding about connecting a theorem to the wind. Topology can sound remote if it is introduced only through rubber sheets and deformed coffee mugs. Those images are useful, but they can leave the subject feeling a little like a clever game played in a room far from ordinary life. Wind returns it to the world. It says no, these ideas are not merely decorative. They describe constraints on things that actually happen around us. The same mathematics that forbids perfectly combed hair on a sphere also whispers that the planet cannot have horizontal wind everywhere at once, and that whisper matters because it reveals what topology is really good at. It does not usually tell you the detailed cause of a phenomenon. It tells you something broader and more durable. It tells you that however the details play out, certain outcomes are forced by the shape of the space itself. That is a rare kind of certainty. Weather is famously difficult to predict in full detail, yet here is a theorem saying something about every possible smooth global wind field on a sphere without needing a single forecast model. This is not magic, it is structure. Let us make the picture a little sharper. Imagine for a moment that the Earth were an ideal smooth sphere, and that at every point on its surface you drew a little arrow showing the horizontal wind. If you insisted that these arrows never vanish, then every point would have to send the air somewhere along the surface. But the hairy ball theorem says that arrangement is impossible. Somewhere, somehow, the arrows must fail to provide a non-zero tangent direction. There must be a point where the horizontal motion drops away. You might try to cheat. Perhaps the arrows could all circulate around the globe in broad bands. Perhaps the atmosphere could agree to move along latitudes and avoid any troublesome dead spots. But the poles immediately spoil that plan. A tangent direction that runs around a line of latitude makes perfect sense away from the poles, yet at the poles those circles collapse. There is no clean horizontal direction of that type left to assign. The singularity returns. Then perhaps you try a different global arrangement. Let the arrows flow from one hemisphere toward the other, always tilting in some consistent way. But once again the sphere closes the trap. Whatever local strategy you choose, the whole surface refuses to support it without some point of vanishing. The atmosphere can be imaginative. The sphere is patient. In the end, topology wins the argument. This is one of those moments where a mathematical fact acquires a kind of dramatic understatement. The theorem does not care how large the winds are elsewhere. You could imagine ferocious motion across most of the globe. You could imagine entire hemispheres alive with flow. Still, somewhere there must be stillness. That is a very strange thing to know about a planet from a theorem that began with hair. It also gives the word calm a new flavour. In daily life, calm sounds like the absence of weather, the pause before the storm, the lucky condition of laundry drying exactly as planned. In the mathematical picture, calm becomes a structural necessity. It is not merely meteorological good fortune. It is the place where the global field acknowledges the topology of the sphere, and that in turn helps explain why the theorem is not trivial, even though the statement is so easy to remember. Many memorable mathematical facts sound simple, only after the right image has been found for them. The deep work lies in understanding what the image is really carrying. In this case, the image of hair conceals the idea of a tangent vector field. The image of a cowlick conceals a singularity. The image of a globe with wind on it reveals that these are not separate metaphors but versions of the same underlying structure. There is another quiet lesson here too. When we speak about wind on Earth, we usually think in terms of causes. Pressure differences drive flow. Rotation deflects it. Temperature gradients create circulation. Oceans influence continents. Day and night matter. Seasons matter. All of that is true and necessary. But topology introduces a different kind of explanation. Not one based on causes unfolding in time, but one based on possibility within space. It tells you not why this particular wind pattern occurred on this particular day, but what kinds of wind patterns are possible or impossible on a spherical world at all. That distinction is useful. Science often works through multiple layers of explanation at once. A meteorologist can explain the immediate physical causes of a cyclone. A topologist can say something about the structure of directional fields on the underlying surface. These are not competing stories. They are different levels of the same world. One tells you how the system evolves, the other tells you what the stage permits. Once you start thinking like that, the skies become more interesting. a broad weather map stops being only a report and becomes a geometric object. Those swirls and bands and calm regions are not just passing conditions. They are patterns living on a sphere, patterns that have to satisfy both physical laws and topological constraints. The planet is not merely wearing weather. It is shaping what weather can look like in very deep ways. And if all this talk of global wind and spherical constraints begins to sound like we're drifting toward more technical language, that is because we are. Not abruptly and not unkindly, but steadily. Up to now we have let hair stand in for direction and wind stand in for flow, because those pictures are faithful enough to carry the intuition. But mathematics eventually wants a cleaner vocabulary. It wants a word for the little arrows lying along a surface. It wants a way to speak precisely about smooth assignment, vanishing points, and how fields behave around them. In other words, to go any deeper than weather maps and patient combs, we need to move from the image to the actual mathematical object the image has been representing all along. Up to this point, hair has been doing a great deal of work for us. It has carried the image, held the intuition together, and given the theorem a memorable shape in the mind. But mathematics eventually asks for a cleaner description. Hair is useful because we can picture it. Mathematics is useful because it can say exactly what the picture means. So now it is time to translate the furry metaphor into the language the theorem is really about. That language is the language of vector fields. A vector, in this setting, is simply a direction together with an amount. You can think of it as a little arrow. The arrow points somewhere, and it has some length. The direction tells you which way something is trying to go. The length tells you how strongly or how far. If you imagine wind on a weather map, each arrow gives you both pieces of information at once. It tells you where the air is moving and how much motion there is. If the arrow is long, the wind is strong. If it is short, the wind is weak. If there is no arrow at all, then at that point the wind is still. That already sounds less mysterious than the terminology might suggest. A vector is not an exotic object. It is one of the plainest tools in mathematics and physics. It is a compact way to describe directed quantity. Velocity is a vector. Force is a vector. Flow is a vector. If an object is moving, if a fluid is drifting, if something is being pushed, vectors are often nearby, behaving efficiently and asking for very little attention. A field is what happens when you assign one of those arrows to every point in a region. If at every location on a flat map you place an arrow showing wind direction and strength, you have made a vector field. If at every point in a room you describe the direction and speed of air movement, that is a vector field. If on the surface of the Earth you assign the horizontal wind at each point, again, a vector field. The field is not one arrow. It is a whole pattern of arrows spread across space. Now the hairy ball theorem can begin to sound a bit more like its formal self. The hairs on the sphere were always standing in for a vector field on the surface. Each little strand lying along the sphere was really a small arrow tangent to the surface. The hair image hid two ideas at once. First, the direction had to lie along the surface rather than sticking out of it. Second, the directions had to vary smoothly from point to point. That is what turned the sphere into more than a fuzzy toy. It made it into a stage for a tangent vector field. That word tangent matters enough to slow down for. A tangent direction on a surface is a direction that stays within the surface at that point. Imagine an ant standing on the sphere. A tangent vector tells the ant which way to walk while remaining on the surface. It does not tell the ant to fly upward or tunnel inward. It tells the ant how to move across the skin of the sphere itself. On a flat plane, every ordinary direction you draw is tangent because the whole plane is flat. On a curved surface, tangent directions depend on location. Each point has its own little set of allowable directions that skim along the surface. This is why the shift from hair to vector fields is more than a vocabulary upgrade. It makes the geometry precise. Hair suggests something lying down on the sphere, but it does not automatically separate the idea of direction from the idea of physical strand. A tangent vector field removes the unnecessary material. No follicles, no density, no texture, no grooming products, and no alarming questions about whether a sphere should have pores, only arrows, only directions and magnitudes assigned point by point along the surface. Once we have that language, several things become easier to state carefully. A perfectly combed hairy ball would correspond to a tangent vector field on the sphere that never vanishes and changes smoothly everywhere. Never vanishes means that at every point the arrow has some non-zero length. In the hair image, that means every hair points somewhere definite along the surface. Changes smoothly means that nearby points have nearby directions and lengths. The field behaves like one coherent pattern rather than a patchwork of unrelated choices. The theorem says that on a sphere this cannot be done. Every continuous tangent vector field on the sphere must vanish at some point. There must be at least one point where the vector has zero length. That is the formal version of the unavoidable cowlick. If the vector is zero, there is no directional arrow there at all. In the hair image, that means there is no clean way for the strand to lie flat in a definite direction. The pattern collapses at that point. Notice how much clearer the 0 point becomes in vector language. A cowlick is memorable, but slightly vague. It might suggest a whirl, a tuft, a crossing, or a small region of bad attitude. A 0 vector is exact. It means the field has no directional push there. The arrow shrinks away completely. That is a singular point in the pattern, not because the surface itself is damaged, but because the field has reached a place where the assignment of a non-zero tangent direction cannot continue. This also helps explain why some pictures of the theorem can look different while still expressing the same underlying fact. One arrangement might show the vectors radiating away from a point. Another might show them circulating around the sphere. Another might produce several singularities rather than one. From the point of view of the theorem, all of these are acceptable examples because the central issue is not the visual style of the field. The central issue is whether a smooth non-zero tangent vector field exists everywhere. On a sphere, it does not. It is worth pausing here because this is the moment where the theorem becomes properly mathematical without losing its intuition. We have not abandoned the image, we have clarified it. Hair was always a way of making a tangent vector field visible to the imagination. Wind on Earth was always a physical example of such a field. Now the pieces line up. The theorem is about tangent vector fields on the sphere. The image of combing hair flat is just the human-friendly way of carrying that statement around. There is a subtle but important distinction between a vector field in space and a tangent vector field on a surface. In ordinary three-dimensional space, you can assign arrows anywhere you like. They may point upward, downward, sideways, or diagonally. There is a great deal of freedom, but on a surface like a sphere, the vectors in the hairy ball theorem are restricted. They must lie within the surface at each point. That is part of what creates the tension. You're not allowed to cheat by letting the arrows lift away from the sphere. The field must live on the surface. If you did allow arrows to point outward, the whole problem would become trivial. Every point on a sphere has a very obvious outward pointing direction. You could simply assign the outward normal direction everywhere and be done. But that would not represent combed hair lying flat. It would represent spikes standing straight out like a planet that has been mildly electrified. Interesting in its own way, perhaps, but not the theorem we are discussing. The hairy ball theorem is about tangent directions, not normal ones. The arrows must stay in the skin of the sphere. Once that condition is in place, the topological obstruction appears, and vector fields give us the exact language to describe it. Instead of saying some hair cannot be combed flat, we say some tangent vector must be 0. Instead of saying the surface keeps a cowlick, we say every continuous tangent vector field on the sphere has at least one 0. The metaphor is gentler, the formal statement is sharper. Both are pointing to the same fact. This is also where the words continuous and smooth deserve careful attention. In everyday speech, those two words blur together, and for the purposes of intuition that is mostly fine. But the basic idea is this. A continuous vector field changes without sudden jumps. A smooth one changes in an even more well-behaved way, with nicely controlled variation. For our present purposes, the important thing is that the field should not jerk from one direction to another unpredictably. Nearby points should have nearby arrows. The field should make geometric sense as a whole. Why does that matter? Because without continuity, you could make absurd assignments that dodge the spirit of the problem. You could point arrows in unrelated directions from one point to the next, and then declare that every point had an arrow. Therefore the theorem must be wrong. But such an assignment would not count as a meaningful field for the theorem. The issue is not whether you can attach random arrows to a sphere. Of course you can. The issue is whether you can do it continuously while staying tangent and never letting the arrows vanish. That is where the impossibility lies. There is another benefit to vector language. It lets us talk not only about direction, but about strength. Hair by itself mostly suggests orientation. Wind, however, has magnitude as well as direction. A vector field naturally captures both. On Earth, a horizontal wind field is not just a collection of directions. Some regions have strong winds, others light breezes, and somewhere perhaps complete stillness. A zero vector then means not merely that the direction becomes ambiguous, but that the horizontal velocity itself is zero at that point. The field has no horizontal push there. That makes the theorem feel more physical, and rightly so. In fluid dynamics, electromagnetism, and many other parts of science, vector fields are fundamental. They describe how quantities vary across space. Velocity fields describe moving fluids. Force fields describe influences acting at points. Magnetic fields describe direction and strength of magnetic effect. The language is broad because the concept is broad. Whenever you want to say what is happening everywhere at once in a directional way, vector fields are usually the natural tool, so the hairy-ball theorem is not some isolated novelty. It is a statement about one of the most common mathematical structures used in science. That is part of why it matters. It tells us something about what kinds of vector fields curved surfaces can support. And once you know that, you start to see related questions everywhere. Can a surface carry a nowhere zero tangent field? If not, how many zeros must appear? What kinds of singularities are possible? How do these questions change when the surface has a hole, or a boundary, or a different topological character? The theorem is one doorway into a much larger conversation. Still, there is value in keeping the doorway visible. When mathematics becomes too comfortable with its own language, it sometimes forgets that its best ideas are often easier to enter through a picture. Hair got us here. The vector field is the actual object. Both are useful. One holds the imagination, the other holds the proof. Let us make the formal picture a little more concrete. Imagine a globe. At every point on its surface, place a tiny arrow tangent to the surface. Suppose these arrows are meant to describe a horizontal wind. Near the equator, they might point east. In mid-latitudes, they might curve around a weather system. Near some singular point, they might become very small. If the field is continuous, then as you move across the globe, the arrows turn and change length gradually. You can stand at one point, look at the arrow there, step a little to the side and see a nearby arrow that is not wildly different. This gradual variation is the visual essence of continuity. Now ask whether it is possible for every single one of those arrows to be non-zero. The theorem says no. Somewhere the arrow must shrink to nothing, not because the atmosphere ran out of enthusiasm, but because the sphere does not permit a continuous tangent vector field without zeros. At this stage, some people naturally ask whether the problem is simply that the sphere is too symmetrical. Perhaps the top and bottom points are somehow special, and if the sphere were deformed into an uneven shape, the obstruction would go away. This is a good question because it reveals exactly what topology contributes. The answer is no. The exact geometric symmetry is not the source of the theorem. A lumpy sphere still has the same topological type as a perfect one, and the same obstruction remains. You can dent it, stretch it, or make it resemble a fruit that has had a difficult week. As long as it remains topologically a sphere, the theorem holds. Every continuous tangent vector field must vanish somewhere. That tells you the statement is not about polished ideal geometry, it is about deeper structure. Vector fields are the object being assigned. Topology is the reason the assignment fails globally. Together they make the theorem precise. There is also a useful contrast between vectors and coordinates. Coordinates are one way of describing where you are. They depend on a chosen system, like latitude and longitude or a grid on paper. Vectors are a way of describing what happens at a point. They live more directly in the geometry of the space. This matters because the hairy ball theorem is not about how you label the sphere. It is about what kinds of tangent directions the sphere can support regardless of labels. Change your coordinate system all you like. Rename north and south. Rotate the globe. The obstruction does not move out of mathematics and into cartography. It stays exactly where topology says it belongs. That is one of the reasons vector fields are such a good language here. They are geometric objects, not just bookkeeping devices. They represent directional structure living on the surface itself. The theorem is therefore saying something intrinsic about the sphere. Not about how we draw it, not about how we measure it, but about the actual possibility of continuous tangent direction on that kind of surface. Once you accept this translation from hair to vector fields, the next step becomes almost inevitable. If the theorem is about zeros of tangent vector fields, then we should look more closely at surfaces that do allow nowhere zero fields, because only by comparison do certain mathematical facts become fully visible. The sphere keeps its unavoidable zero, but not every surface does. Some shapes admit smooth tangent vector fields everywhere without complaint, and when one of those shapes appears, it becomes immediately obvious that the theorem is not merely about directional smoothness in general. It is about the specific topological character of the sphere. In other words, to understand what the vector field is really running into, we now need a surface that behaves differently enough to expose the true source of the obstruction. And this is where the story becomes especially revealing, because once you place the sphere beside a donut-shaped surface, something very quiet and very important comes into view. At first glance, the two objects do not seem remotely alike. One is compact, closed, and rounded in the simple way children draw planets, bubbles, and marbles. The other has a hole through its middle and carries the unmistakable silhouette of breakfast, ceramics, and certain life choices made near a bakery. To the eye, they appear quite different. To the hand, they feel different. To everyday common sense, they belong in different categories entirely. And yet, from the point of view that matters here, the difference between them is not one of style or curvature or visual complexity. It is one quiet topological fact. The sphere has no hole. The donut does. That single difference changes everything. It changes what kinds of smooth direction fields the surface can support. It changes whether a nowhere zero tangent vector field is possible. It changes whether the hairy ball theorem applies in the familiar way. On a sphere, no matter how carefully you try to arrange the arrows, some point must be left with zero direction. On a donut-shaped surface, that obstruction disappears. You can comb a hairy donut flat. It is difficult to overstate how useful this comparison is. When a theorem is first introduced through one shape alone, it can be tempting to treat the result as a curious quirk of that one example. A sphere keeps a cowlick. Fine. Spheres are awkward. End of story. But the moment you set the sphere beside a torus, which is the formal mathematical name for the donut-shaped surface, the deeper logic starts to show itself. The theorem is no longer about roundness in some vague everyday sense. It is not about smooth objects being difficult. It is not about all curved surfaces having bad manners. It is about topology. The whole matters. The absence of the whole matters, and the surface behaves accordingly. Let us sit with the donut for a moment, because it deserves to be seen clearly. A torus is the surface you get if you take a circle and sweep it around in space, making a ring. It has an outer side, an inner side, a top, a bottom, and most importantly, a central opening. That opening is not decorative. It is the deep, not a visual flourish. It is the deep structural feature that sets the torus apart from the sphere. Now imagine covering this donut-shaped surface with tiny hairs and trying to comb them flat. Suddenly, the problem that plagued the sphere begins to relax. You can choose a direction that runs all the way around the donut, following the circular path around the ring, and every point on the surface can participate. No singularity is forced. No point must lose its direction. The hairs can all lie smoothly along the surface in one continuous pattern. The donut does not insist on a cowlick. This is one of those moments in mathematics that feels almost impolite in its clarity. The sphere refuses, the donut agrees, and the reason is not hidden in complicated machinery. It sits there in the shape itself, in the quiet but decisive fact that one surface encloses its interior without a hole, while the other loops around one. The comparison is useful partly because the surfaces do share some features. Both are smooth, both are closed in the sense of having no boundary edge. Both live happily in ordinary three-dimensional space. Both can be imagined as surfaces an ant might walk on forever without falling off an edge. Yet one supports a nowhere zero tangent vector field, and the other does not. So whatever causes the obstruction on the sphere cannot simply be smoothness, closedness, or the ability to curve. It has to be something more particular. That something is the topological type of the surface. This is where topology shows its character beautifully. It notices that the difference between these objects is not mainly in their exact geometry, but in their global connectedness. The sphere can be continuously deformed into many other sphere-like shapes without changing its essential topological nature. Stretch it, squash it, dent it gently, and it is still topologically a sphere. The torus too can be stretched and bent into many ring-like forms without ceasing to be a torus. But no amount of smooth deformation will turn a sphere into a torus unless you tear the surface or punch a hole through it. The hole is not negotiable, it is a topological fact, and because it is a topological fact, it controls the behaviour of vector fields in a topological way. One very good way to feel this is to think in terms of roots. On a sphere, every loop can eventually be shrunk down to a point without tearing the surface. Draw a circle around some region of the sphere and, at least in principle, you can contract that loop smaller and smaller until it disappears into a point. The sphere has no essential loop that must remain open. On a torus, some loops cannot be shrunk that way. A loop going around the hole remains trapped by the hole. It cannot collapse to a point without cutting through the surface or tearing it. That trapped loop is a sign that the torus has a deeper directional structure available to it. In less technical language, the torus has room for a continuous direction to circulate forever without being forced into a dead end. A sphere does not. Every attempt to continue a direction field globally on the sphere eventually runs into the fact that the surface closes too simply. There is nowhere for the direction to keep threading itself without contradiction. On the torus, the central hole opens a kind of topological corridor. The field can wrap around the surface coherently. If that sounds a little poetic, the practical picture is actually very ordinary. Think of the donut as having one natural direction that simply goes around the ring. Every point on the surface can participate in that circulation. The arrows can all point around the central opening, never needing to collapse. You can walk an ant along those directions forever and never reach a place where the rule fails. The field is smooth, it is tangent to the surface, it is nowhere zero. The donut has been combed. Try the same level of global consistency on the sphere, and the old problem returns. There is no equivalent around the ring direction because there is no ring. No central hole gives the field a path to follow without obstruction. The surface closes too completely. The directional pattern has to account for all of it, and somewhere the assignment breaks down. This comparison is often the first place where people begin to trust topology, not just as a collection of amusing analogies, but as a serious way of seeing. Because the difference between the sphere and the torus is not superficial, it has consequences. Real, mathematical consequences. The kinds of fields, flows, textures, and structures each surface can support are different, because the surfaces themselves are different in a deep, stable way. That stability matters. Suppose you deform the torus a little, make it lopsided, Thicken one side, flatten the top. Turn your elegant mathematical donut into something more like a ring-shaped cushion that has endured several years of poor treatment. It remains a torus. The hole is still there. And because the hole is still there, the nowhere zero tangent field is still possible. Likewise, if you take a sphere and make it perfectly round, you do not thereby give it the gift of a smooth global combing. It is still topologically a sphere. The cowlick remains unavoidable, so the difference between the two shapes is not fragile. It does not depend on ideal symmetry or polished geometry. It survives deformation. That is one of the deepest signs that we are in topological territory. When the exact metrics can change while the essential possibility remains the same, topology is usually nearby, quietly pleased with itself. There is another way to see the contrast, and it involves the idea of balance. On the sphere, singularities are not optional because the total topological bookkeeping demands them. The surface imposes a non-zero total, so some zeros of the vector field must appear. On the torus, the bookkeeping comes out differently. The total obstruction that forced singularities on the sphere vanishes. That does not mean singularities are forbidden on a torus. You can certainly create vector fields on a torus that have zeros if you want them. But unlike on the sphere, they are not mandatory. The torus allows you to avoid them entirely. This is a subtle but important point. The theorem about the sphere is an impossibility theorem. The torus gives you a possibility theorem by contrast. Together they show that the real issue is not whether singularities can exist, but whether the surface requires them. The sphere says yes, the torus says no. That quiet difference has enormous explanatory power. It tells us, for instance, that if we want to understand why certain defects appear in directional patterns on surfaces, we cannot simply blame the local geometry. We have to ask what kind of surface we are dealing with globally. A defect may be unavoidable on one surface and entirely avoidable on another. The same kind of local behavior can live inside very different topological worlds. This is one reason computer graphics and geometry processing often run into these ideas whether they intended to or not. If you are assigning directions across a digital surface, perhaps to guide texture, shading, animation, or flow lines, the topology of that surface matters. A sphere-like model cannot carry a smooth, non-vanishing tangent field everywhere. A torus-like model can. The mathematics does not stop at blackboards. It follows the shape into applications and waits there. The comparison also helps clear away a very common misunderstanding. People often hear that the hairy ball theorem concerns even-dimensional spheres, and conclude that the crucial feature must be dimension in a vague sense, or perhaps curvature, or perhaps some mysterious quality of round things. The sphere versus torus contrast teaches a sharper lesson. What matters immediately to our intuition is not roundness, but topological structure. A torus can be quite curved in places. It may even look more complicated than a sphere, yet it behaves more generously with respect to tangent vector fields, because its topology is different. This is exactly the kind of thing topology loves to reveal. The surface that looks simpler may impose the stronger restriction. The surface that looks more elaborate may actually permit more freedom. Appearance is not useless, but it is not the final judge. The deeper organization of the surface decides what kinds of smooth global patterns are available. At this point, it becomes tempting to ask whether every hole improves the situation, and in a certain broad sense, that question leads into a larger classification story. Surfaces can have different numbers of holes, and those differences affect the kinds of vector fields they support. But even without wandering into the full taxonomy of surfaces, the first contrast is enough to change how one sees the theorem. The sphere is no longer an isolated curiosity. It is one case in a landscape of surfaces whose global properties shape what fields can live on them. And once that landscape comes into view, the sphere starts to look almost stern in comparison. It is smooth, balanced, and perfectly respectable, yet it forbids the field you want. The torus, with its extra opening and slightly more adventurous topology, is the one that behaves helpfully. There is a small comedy in that. The simpler looking shape is less cooperative, The pastry wins. Still, the point is not to mock the sphere. The point is to understand what its refusal teaches. By failing to support a nowhere-zero tangent field, the sphere announces that topology places real constraints on smooth structure. By contrasting it with the torus, we learn that those constraints are not universal to all surfaces. They arise from the specific nature of the surface involved. The theorem becomes less like an isolated trick and more like an example of a general law. Shape governs possibility. It is also worth noticing how gentle this law can appear from the outside. The sphere and the torus are not violently different objects. They are both closed surfaces you can picture easily. No wild fractal complexity is needed, no labyrinth of dimensions. One hole is enough to change the answer. That is perhaps one of the most elegant features of topology. Enormous differences in global behavior can hinge on very small-looking structural changes. If you imagine the sphere and the torus made of infinitely flexible rubber, you can deform each one in many ways, but you cannot pass from one to the other continuously without a dramatic act. Something has to happen. A puncture, a tear, a hole, a joining. Topology records those dramatic acts, not the cosmetic ones. And the hairy ball theorem is sensitive exactly to that level of change. This is why the quiet difference matters so much. It is not just a difference in classification, it is a difference in what can exist on the surface. On the sphere, every continuous tangent vector field must vanish somewhere. On the torus, there are continuous tangent vector fields with no zeros at all. That is as clear a topological contrast as one could reasonably ask for. And from there, another important thought begins to form. If the sphere must keep a cowlick, and the torus can escape one, then the really interesting objects are not just the surfaces themselves, but the places where order breaks down when a surface does demand it. Singularities are no longer mere failures of arrangement. They become the visible markers of topological necessity. They tell you where the surface has forced the field to acknowledge its limits. On a sphere, they are unavoidable. On a torus, they are optional. And that means the singular point, the swirl, the still spot, or the collapse of direction is not just a nuisance. It is information. It is the surface speaking through the field. That is where the next layer of the story begins, because once you start looking at those forced irregularities as meaningful rather than embarrassing, you can ask a better question. Not simply why some surfaces allow them and some do not, but what those singularities actually are, how they behave, and why the breakdown of order often turns out to be the most structured part of the whole picture. Once you start looking at those forced irregularities as meaningful rather than irritating, the whole subject becomes much more interesting. Up to now, the troublesome point on the sphere may have seemed like the awkward leftover, the one patch where order failed to complete the job. But in mathematics, the places where order breaks are often the places where the structure becomes most visible. The singularity is not just where the pattern gives up, it is where the pattern tells the truth about the surface it lives on. That word singularity can sound heavier than it needs to. In popular science, it sometimes arrives wrapped in dramatic lighting, usually accompanied by black holes, collapsing stars, and a voice that would like you to take a moment to be suitably impressed. Here, though, a singularity is something gentler and more local. It is simply a point where the smooth directional field cannot continue in the ordinary way. The arrows may vanish there, or the surrounding directions may swirl around it in a manner that makes the center impossible to define as an ordinary non-zero tangent vector. It is a special point because the regular pattern breaks down there, but special does not necessarily mean catastrophic. Often it just means informative. In the hairy ball picture, the singularity is the cowlick, the whirl, the stubborn spot where brushing no longer produces one clean local direction. In the wind on earth picture, it is the calm point where the horizontal wind drops to zero. In the more formal language of vector fields, it is a zero of the field, a place where the arrow has no length. Different pictures, same underlying idea. The field behaves smoothly over much of the surface, then reaches a point where the usual local rule cannot be maintained without interruption. What matters most is that singularities are not all alike. This is where the subject becomes more textured than the simple sentence of the theorem first suggests. It is one thing to say that some bad point must exist. It's another to notice that there are different kinds of bad points, each with its own local character. Mathematics cares deeply about that local character, because it turns out not all breakdowns contribute in the same way to the global bookkeeping of the field. Take the simplest picture first. Imagine arrows on a surface pointing outward from a central point in all directions, like water spreading from a spring. Everywhere around that centre the arrows are clear and orderly, but at the exact centre there is no single non-zero tangent direction that fits. That centre is a singularity. Or reverse the picture and let all the arrows point inward, like water draining toward a sink. Again, the centre is singular. In both cases, the surrounding field has a strong radial flavour. The arrows either flow away from the point or into it. Now imagine a different sort of pattern. Instead of radiating in or out, the arrows swirl around a point. They circle it, turning smoothly as they go. Once again, the centre itself becomes special. The surrounding field is well behaved, but the exact middle cannot be assigned a non-zero direction in the same smooth way as the rest. That too is a singularity, but it feels different from the source or sink picture. The surrounding order has a different local geometry, and then there is the saddle-type behaviour, which is perhaps less famous in ordinary life but very important in mathematics. Here the arrows may approach the point along some directions and move away along others. The pattern feels balanced in a different way, more like a crossroads of conflicting tendencies than a simple in or out flow. If you were expecting every singularity to be a little whirl or a neat circular tuft, the saddle reminds you that breakdowns can be organised in several distinct ways. This matters because when mathematicians study vector fields on surfaces, they do not just count singularities as though each one were the same sort of pebble in a jar. They ask what kind of singularity each point is, how the surrounding directions behave, and what contribution that local structure makes to the whole surface. The global theorem is supported by very local information. Each singular point carries a little piece of the total story. One of the best ways to feel this without getting dragged into technical machinery is to imagine walking in a small loop around a singularity while watching how the arrows turn as you go. On an ordinary regular patch with no singularity inside the loop, the field may wiggle or curve, but there is no special topological drama. Around a singularity, however, the directions can wind around in a more meaningful way. By the time you return to your starting point, the arrow may have effectively turned through a full cycle relative to your motion around the loop. Different singularities create different winding behaviour. The winding is not an accidental flourish, it is a local signature. And signatures matter because the surface as a whole keeps score. On a sphere, the total contribution from all singularities has to come out a certain way. You may have one source like point, you may have two whirls and a saddle, you may arrange the field to spread the trouble around in a pattern that looks elegant, awkward, or almost decorative depending on your mood. But the total cannot be cheated. The sphere requires a specific balance, and that is why the singularities cannot all disappear. This is one of those cases where mathematics turns what looks like disorder into a more refined kind of order. At first, the singularity seems like the opposite of structure. It is the place where the regular field fails. But look closer, and the failure itself has pattern. The singularity is not chaos. It is a governed exception. The arrows around it behave in a way that can be classified, understood, and woven into a global theorem. The place where order breaks turns out to have its own order. That is a recurring theme in mathematics and physics. A defect is often not random damage. It can be a stable, meaningful feature of a system, something that carries information about the larger constraints in play. A knot in a rope, a vortex in a fluid, a dislocation in a crystal, a domain wall in a material, all of these are places where the local arrangement differs from the simple uniform pattern. Yet they are often the most informative places in the system. They reveal tensions, symmetries, and conservation laws that would remain hidden if everything looked perfectly smooth. The singularities in vector fields on surfaces behave in much the same way. They are the visible traces of topological necessity. If the surface permits a perfectly smooth nowhere zero field, as the torus does, then singularities are optional. If the surface forbids such a field, as the sphere does, then singularities become compulsory witnesses. They are not signs of poor craftsmanship. They are the places where the topology becomes visible. This changes the emotional flavour of the theorem quite a bit. It stops being a story about failure and becomes a story about unavoidable structure. The cowlick on the hairy sphere is no longer the embarrassing last mistake. It is the mathematical equivalent of a footprint. It tells you something passed through here. It tells you the field could not flatten itself globally because the surface did not allow it. The singularity is evidence. You can see why physicists and applied mathematicians often become very interested in defects and singular points. In the idealized version of a problem, uniformity looks nice. In the real version, the defects often carry the interesting behavior. Weather systems swirl. Fluids form vortices. Magnetic materials organize into domains with boundaries between them. Liquid crystals develop defects where orientation breaks down. Even in computer graphics, when one tries to assign smooth directions over a surface for texture or shading, singular points often appear because the surface topology insists on them. In each case, the defect is not just an inconvenience to be patched over, it is part of the geometry of the problem. Whirls are especially appealing examples because they are so visual. We already know them from human hair. Many people have a natural spiral pattern on the crown of the head, a place where the hair seems to arrange itself around a centre rather than obediently choosing one straightforward direction. It is not a perfect mathematical singularity, of course, because a human scalp is not a perfect sphere, and real hair is a biological negotiation rather than a tangent vector field. Still, the resemblance is close enough to be useful. The world gives intuition. It shows how order around a point can be completely sensible, while the centre itself resists flattening into the same simple local rule. Spiral weather systems provide a larger scale version of that intuition. So do vortices in water when liquid drains from a sink or swirls around an obstacle. The motion may be smooth around the centre, yet the centre is special. It anchors the pattern. Remove it conceptually, and the organisation of the surrounding flow changes. Again, the singularity is not just where the field is missing, it is what gives the nearby field its shape. Saddles are subtler, but perhaps even more revealing. A saddle-type singularity does not announce itself with obvious circular motion. Instead, it has a sort of directional tension. Along some paths, the arrows approach the point. Along others, they move away. The pattern is less immediately picturesque than a whirl, yet it plays a crucial role because saddles contribute differently to the topological bookkeeping. This is one reason mathematics insist on classifying singularities, not merely spotting them. Two bad points can cancel or combine in ways that depend on their local type. If you only counted raw locations and ignored their structure, you would miss the whole mechanism. This is also where the subject acquires a slightly surprising elegance. The field can be redesigned locally. Singularities can move across the surface as the vector field changes. Two singularities can drift toward one another. Some can merge into new patterns. Yet through all of this local motion and rearrangement, the total topological requirement remains fixed for the surface. The local drama changes. The global law does not. That constancy is one of the reasons topology feels so different from ordinary geometry. In geometry, you may focus on lengths, angles, and exact shapes, all of which can change under deformation. In topology, what matters is often more durable. You can stretch the surface, shift the field, move the singularities around, and still the total topological burden stays put. The individual characters in the story may enter from different doors, but the plot refuses to change. Another helpful way to think about this is to imagine that the surface is charging a tax for smooth global organisation. On a torus, the tax can be zero, so a nowhere zero tangent field is possible. On a sphere, the tax is non-zero, so singularities must be paid in. You can choose the denomination. One source like point perhaps, or two simpler whirls and a saddle, depending on the field. But the total payment cannot be avoided. This is not the formal language, naturally, but it captures the right kind of inevitability. Singularities are how the field pays the surface what it owes. That makes the places where order breaks oddly respectable. They are not the wild edges of a failed pattern. They are the points where the pattern fulfills its topological obligation. Once you see them that way, you stop wanting to erase them and start wanting to understand them. There is a quiet lesson in that for mathematical thinking more generally. The first reaction to an irregular point is often annoyance. Something has gone wrong. But good mathematics has a habit of asking whether the irregularity is actually the main event. What if the defect is not noise but signal? What if the break in order is the clue that tells you what kind of order was possible in the first place? The hairy ball theorem becomes much richer once you adopt that attitude. The singularity is no longer the blemish, it is the message. This is why topological defects show up across so many areas of science. Systems that try to organize themselves smoothly over a space often discover that the space has opinions. The resulting defects are where the impossible becomes visible. They are often stable because there is no local trick that can simply remove them. To get rid of them, you would have to change the global structure or introduce another defect with the right complementary behavior. The system is not merely sloppy, it is constrained. On the sphere, every smooth tangent vector field is constrained in exactly that way. The singularities may sit quietly at the poles in one example. They may arrange themselves in a more interesting pattern in another, but they cannot all be combed away. The order of the field is always built around these unavoidable points of breakdown, and because those points are so informative, they become a natural bridge to a much larger idea. The hairy ball theorem is not just telling us something cute about one awkward kind of surface. It is pointing toward a general principle. The global shape of a space governs what kinds of smooth structures it can support, and the places where those structures fail are often the most direct evidence of that governance. Singularities are not random accidents scattered across a pattern. They are the local face of a global rule. This is why the theorem has lasted so well in the mathematical imagination. It is memorable because of the image, useful because of the formal statement, and deep because of what it reveals about order and its limits. It says that even a beautifully smooth surface may refuse a beautifully smooth field. It says that the breakdown can be unavoidable. And it says that the unavoidable breakdown is not meaningless. It has type, structure, and topological significance. Once you absorb that, it becomes difficult to look at the theorem as merely a curiosity. It begins to look more like a template, a compact example of how mathematics often works at its best. A simple image leads to a precise statement. The precise statement opens into a broader theory. The broader theory turns what looked like a nuisance into a central object of study, and along the way, one learns to trust that the strange little exceptions in a system are often the parts worth following most carefully. That trust matters, because the next step is not just to admire the singularities themselves, but to ask what they tell us about the larger world. If a sphere cannot support perfect global directional order, and if the singular points are the honest markers of that limitation, then the theorem is really about more than hair, weather, or even vector fields. It is about the way structure places limits on what reality can do, and about how those limits appear not as dramatic barriers, but as small, unavoidable facts built into the fabric of a shape. Once you start seeing the theorem that way, it stops being only a statement about what cannot be done to a sphere, and starts becoming a statement about the sort of world we live in. Not because the universe is secretly made of hairy tennis balls, though that would certainly improve some museum exhibits, but because the theorem captures a general truth that shows up again and again in science. Reality is full of systems that try to organize themselves smoothly across space, and just as often, the shape of that space quietly places limits on what kind of order is possible. That is one of the most useful habits mathematics can teach. It teaches you to stop assuming that every irregularity is a mistake. Sometimes the irregularity is the evidence that a deeper rule is in effect. Sometimes the failure of perfect order is not a sign that the system is broken, but a sign that the system has run into a structural boundary it cannot cross. The hairy ball theorem is a very compact example of that idea. On the surface, it is almost comical. You cannot comb a hairy sphere flat without leaving at least one bad spot, but under that image is a stronger lesson. A smooth global pattern can be impossible not because the local pieces are badly behaved, but because the whole space refuses to support it. That is the sort of thing that turns out to matter far beyond the original image. Take something as ordinary as the weather. We have already seen that a smooth horizontal wind field on a sphere must vanish somewhere. That sounds like a neat application, and it is, but it is also part of a bigger point. The atmosphere is not just moving according to pressure and temperature and rotation. It is moving on a world with a specific shape. The same physical laws acting on a different topological surface would allow different large-scale patterns. In that sense, the theorem reminds us that reality is not only about forces and matter, it is also about the spaces those forces and materials inhabit. This is easy to overlook because most of the time, shape seems like a passive background detail. A surface looks like the stage on which the real action happens. The theorem quietly corrects that assumption. The stage is not passive. The stage has rules. The shape of a thing influences what kinds of smooth structures can exist on it. A surface is not just where events happen. It helps decide which events are even possible. That idea is not limited to wind. In physics and materials science, many systems are described by fields of orientation or flow. Molecules in liquid crystals tend to align in local directions. Spins in magnetic materials prefer certain arrangements. Defects appear where that local order cannot be extended globally without interruption. These defects are not random imperfections you could remove if only the laboratory were neater or the experiment were kinder. Very often they are required by the geometry or topology of the system. This is one of the reasons topological thinking has become so influential in modern science. It provides a language for constraints that do not come from the detailed chemistry or exact local forces alone. It tells you that some features of a system are robust because they are protected by the global structure. They survive noise, distortion, and imperfection because they are not delicate local accidents. They are consequences of the way the whole thing is put together. The hairy ball theorem gives a simple version of that insight. You can deform the sphere. You can make it imperfectly round. You can imagine it as a globe, a fruit, or a lumpy rubber toy with a manufacturing defect. None of that changes the central fact. If it is still topologically a sphere, the obstruction remains. That robustness is part of what makes the theorem feel so satisfying. It is not a fragile curiosity. It is a stable truth about a kind of space. And that word stable matters if we are talking about reality. Scientific systems are almost never perfect. Real objects have noise, roughness, thermal motion, asymmetry, and 1,000 little departures from ideal textbook conditions. If a mathematical truth vanishes the moment the system becomes slightly imperfect, then it is elegant, but perhaps not very deep. If the truth survives those imperfections, then it begins to look like something genuinely structural. The hairy ball theorem survives. That is why it reveals something real. It also reveals something about how science works when it is going well. There is a common picture of science in which progress comes from measuring more and more precisely, calculating more and more carefully, and piling up detail until the world finally explains itself. There is some truth in that, of course. Precision matters. Detail matters. But there is another part of science that works by identifying what details do not matter for a certain question. Topology is especially good at this. It tells you that for some problems, the exact curvature, size, and symmetry are not the deciding factors. The global connected structure is. Once you know that, you stop chasing the wrong details. That is a powerful kind of understanding. It is one thing to know how a specific pattern behaves. It is another to know which patterns are impossible before you even start trying to build them. The theorem gives that kind of knowledge. It says there is no need to search forever for the perfect, smooth, nowhere zero tangent field on a sphere. It does not exist. The effort would be misplaced. The boundary is structural. There is something very practical about that, even if it arrives in highly theoretical clothing. Engineers, physicists, and computer scientists all benefit from knowing the difference between a problem that is hard and a problem that is impossible for topological reasons. In graphics, for example, assigning smooth directions across a surface matters for texture mapping, animation, and geometry processing. If the model is sphere-like, then singularities in the direction field are not necessarily signs that the algorithm is poor. They may be unavoidable. Good design then means placing and managing those singularities intelligently, not pretending they can be eliminated altogether. That is another quiet lesson the theorem offers. Once you know a defect is unavoidable, the question changes. You stop asking how to remove it completely and start asking where it should go, how it should behave, and how its effect can be controlled. That is a much more mature question. It shows up in mathematics, in science, and in ordinary life more often than one might like to admit. Some constraints are not there to be defeated. They are there to be understood and handled well. The theorem also reveals something about the relationship between local experience and global truth. Locally, the sphere seems innocent. Any small patch looks almost flat. Any small patch can be combed. Any small patch can support a neat little directional arrangement. If your experience were limited to local patches, you would never suspect a global problem. This happens constantly in the sciences. Local approximation works beautifully. Then someone asks whether the approximation can be extended to the whole system, and suddenly a hidden obstruction appears. That gap between local success and global impossibility is one of the most important patterns in mathematics. The hairy ball theorem makes it visible in a very concrete way. It tells you that the world can look manageable in every small neighborhood and still resist a single global rule. That is not because the local observations were wrong. It is because local truth is not always enough. The whole can carry constraints that no part reveals by itself. That lesson reaches farther than topology. In differential geometry, in physics, in complex systems, and even in the practical business of modeling real phenomena, one constantly runs into situations where local consistency does not guarantee global compatibility. Small-scale evidence can be completely correct and still fail to predict the behavior of the whole. The theorem is a compact reminder to be suspicious of local intuition when the system lives on a non-trivial global structure. Another thing the theorem reveals is that mathematics does not always progress by making reality more complicated. Sometimes it progresses by finding the right simple picture for a deep fact. Hair on a sphere is not sophisticated language. That is precisely why it works. It lets the mind hold a topological obstruction in one ordinary image. Good mathematics often has this quality. It takes a truth that might otherwise remain buried under layers of technical language and gives it a form the imagination can revisit easily. That does not mean the theorem is shallow. Quite the opposite. The better the image, the more room there is underneath it for serious structure. The hairy ball theorem is a small doorway into broader ideas about topology, vector fields, singularities, and the way global invariants control local behavior. It also connects naturally to one of the larger themes in modern science, which is that not every property of a system depends on the fine details. Some depend on topology, and topology tends to be stubborn. This stubbornness is part of what makes topological reasoning so attractive in physics. If a phenomenon is topologically protected, then changing it requires more than a slight perturbation. You have to alter the deeper structure. That kind of protection explains why certain defects, modes, or configurations persist under ordinary disturbances. The hairy ball theorem is a comparatively gentle example, but it carries the same flavour. You do not remove the unavoidable zero on a sphere by brushing more carefully. You would have to change the topological kind of the surface itself, and that leads to one of the theorem's most revealing comparisons. The difference between the sphere and the torus is not cosmetic. The torus has a hole, and that hole changes what directional fields the surface can support. This tells us that very small seeming changes in topology can produce very large changes in possibility. A hole is not just an opening, it is a structural modification with consequences for everything from vector fields to loops to the organisation of flow. That is a striking thing for mathematics to be able to say. It means the world is not merely sensitive to quantities, it is sensitive to qualitative shape. Not all differences are matters of more or less. Some are matters of kind. A torus is not just a sphere with a little extra personality. It is a fundamentally different topological object, and the theorem responds to that difference immediately. There is another reality the theorem reveals, and it is about explanation itself. We often think of explanation as a causal story. This happened because that force acted, this current flowed, that pressure changed. Those are good explanations. Science needs them. But topology offers another kind. It offers structural explanation. It says this arrangement cannot exist because the space forbids it. That is not a story about causes unfolding over time. It is a story about the architecture of possibility. Both kinds of explanation matter. In many real systems, causal laws determine how the system evolves, while topological laws determine what kinds of overall patterns are available in the first place. The hairy ball theorem belongs to that second category. It does not tell you how a given wind field developed. It tells you that no smooth horizontal wind field on a spherical surface can avoid a zero. The theorem is not replacing the ordinary physics. It is sitting underneath it, defining part of the space of allowable behaviour. That layered view of explanation is one of the most mature things mathematics can offer reality. It reminds us that the world is organised on more than one level. There are local interactions, detailed mechanisms, conservation laws, symmetries, and then there are topological constraints that care very little about the fine print. Sometimes the deepest understanding comes from knowing how those levels fit together rather than expecting one of them to do all the work. It is also worth noting that the theorem reveals something about what elegance in science really means. Elegance is often misunderstood as simplicity without residue, a perfect pattern with no awkwardness left over. But many of the most elegant scientific truths do not remove awkwardness. They explain why a particular awkwardness must be there. The unavoidable singularity on the sphere is not a blemish on an otherwise elegant picture. It is part of the elegance. It is the price the surface charges for global consistency. That is a valuable correction to a very common instinct. We tend to admire uniformity and distrust exceptions. We like the idea that the best theories make everything smooth, continuous, and neatly resolved. Often they do not. Often they show that certain exceptions are mandatory. Once you understand the rule, the exception becomes not less beautiful but more so. The singularity is where the theorem becomes visible. That way of thinking has a curious side effect. It makes one more patient with irregularity, not in the sense of becoming vague or careless, but in the sense of asking a better question before assuming something is wrong. Is this defect accidental, or is it required by the structure of the system? Is this singularity removable, or is it carrying essential information? The theorem trains that habit of mind very effectively because the answer in this case is so clear. The bad spot is not a failure of grooming, it is the honest shape of the solution. There is a broader philosophical temptation here, of course, and it is best handled carefully. One could try to turn the theorem into a sweeping metaphor about life, complexity, or the impossibility of perfect order. That can be done, but too much of it usually makes the mathematics worse rather than better. The theorem is valuable because it is precise. It does not vaguely suggest that all order is doomed. It says something exact about a particular kind of field on a particular kind of surface. That precision is what gives the larger resonance any legitimacy at all. If you let the theorem become too abstract in the ordinary literary sense, it loses the very thing that made it worth listening to. Still, even without forcing it into philosophy, the theorem does encourage a more grounded insight. It reminds us that the world is structured in ways that are not always visible from close range. It reminds us that some limitations are not failures of method but facts of architecture. And it reminds us that the smallest stubborn point in a pattern can reveal something true about the whole space. That is not only mathematically satisfying, it is scientifically useful. It gives us a model of what it means to understand a system well. Understanding does not always mean controlling every detail. Sometimes it means knowing where control must fail and why. The hairy ball theorem does that with almost unreasonable efficiency. In one image, it captures the relation between local smoothness and global obstruction. In one statement, it reveals the topological power of shape. In one amusing name, it hides a serious lesson about fields, surfaces, singularities, and the architecture of possibility. And perhaps that is why people keep coming back to it. Not because it is the grandest theorem in mathematics, or the most technically difficult, or the one with the largest practical empire, but because it teaches something very clearly. The world does not only consist of things and forces, it also consists of spaces with structure, and that structure decides what kinds of order can live there. Once you learn to see that, the theorem stops being about hair almost entirely. It becomes a small but very clear window into the way mathematics reaches into reality and tells us not just what happens, but what can happen at all. And once you're standing at that window, it is hard not to look back at the theorem one more time and ask the closing question that has been quietly waiting underneath all the others. If a sphere cannot be perfectly combed, if singularities are not mistakes but necessary markers of structure, and if topology can reveal such limits with so little fuss, then what exactly is the final lesson of this strange little theorem about the relationship between order, impossibility, and the shapes that govern both? By now, the theorem has done something rather unusual. It began as a joke that sounded almost too playful to belong to serious mathematics, and it has ended up teaching us something exact about surfaces, vector fields, weather, singularities, and the quiet authority of topology. That is quite a journey for a sentence about combing hair, and perhaps the most satisfying part is that the central idea never really changed. The language became more precise, the examples became broader, the consequences became deeper, but the heart of it remained stubbornly simple. Some things can never lie flat, not because we have failed to arrange them properly, but because the shape underneath them will not allow it. That is the last strand worth holding on to. A sphere is such a familiar object that it is easy to underestimate how much structure it carries. We meet spheres everywhere. Balls, bubbles, fruit, planets, droplets, beads, marbles, and all the little rounded objects that sit quietly in the world without announcing that they are mathematically significant. A sphere feels complete, balanced, almost too ordinary to be interesting, and yet it hides a very definite rule. If you try to place a smooth tangent direction at every point, never letting that direction vanish, the sphere says no. Somewhere, at least one point must resist. Somewhere, the field must break. Somewhere, the hair refuses full obedience. That refusal is what the entire story has been about, not just the fact that the bad spot exists, but what kind of fact it is. It is not local clumsiness. It is not poor planning. It is not the result of using the wrong comb, the wrong strategy, or the wrong level of determination. It is structural. The sphere does not reject perfect global order, because the attempt was sloppy. It rejects it because the attempt aims at something the surface does not permit. There is a certain relief in that kind of impossibility. Mathematics does not shrug and say, perhaps with more effort. It says this arrangement cannot be completed on this surface, full stop. That kind of clarity is one of the great pleasures of the subject. It removes the false mystery and leaves behind the real one. Not why did the attempt fail, but why does the shape enforce that failure so cleanly? The answer, as we have seen, is topology. Not the exact measurements, not the local curvature in the everyday sense, not the polished geometry of a perfect globe, but the deeper structure of the surface. The sphere has no hole, the torus has one. That quiet difference changes everything. On the sphere, singularities are mandatory. On the torus, they are optional. That comparison may be one of the most useful things the theorem gives us, because it shows that the issue is not about awkwardness in general. It is about the kind of world the field is trying to inhabit. Once you see that, the theorem stops feeling isolated. It begins to look like a representative of a much larger family of truths, all of them saying in one way or another that space is not neutral. Surfaces are not passive backdrops. Shape is not mere decoration. The structure of a space limits the structures that can live on it. Fields, flows, orientations, and patterns all have to negotiate with the world they occupy. Some negotiations end smoothly, others end in singularities, and singularities in the end have turned out to be far more respectable than they first seemed. At the beginning, the bad spot on the hairy sphere looked like the nuisance, the flaw, the one place where the neat picture broke down. But mathematics, being reliably unimpressed by first impressions, asked a better question. What if that point is not the flaw in the picture? What if it is the most honest part of it? What if the breakdown is where the true structure finally becomes visible? That question changes everything. Once the singularity is understood as necessary, it ceases to be an embarrassment. It becomes evidence. It tells you that the surface is being itself, that the field has reached the limit of what topology will allow, and that the local pattern is answering to a global rule. The cowlick is no longer the thing that spoiled the arrangement. It is the mark that proves the arrangement belongs to a sphere. This way of thinking is useful far beyond the theorem itself. It teaches a habit that mathematics returns to again and again. Do not treat every irregularity as noise. Sometimes the irregularity is where the deepest law is showing through. A calm point in a wind field, a defect in a material, a singularity in a flow, a place where a smooth pattern cannot continue. These are not always signs of damage. Sometimes they are the inevitable places where the underlying structure declares itself. That is one reason the theorem feels bigger than its statement. It is precise, but it points beyond itself. It shows how local order can coexist with global impossibility. It shows how a system can behave beautifully in every small neighborhood and still refuse a single flawless arrangement across the whole. It shows how a simple object can carry a non-trivial obstruction. And it shows how a silly-sounding metaphor can hide a serious theorem without losing any of its seriousness. There's also something quietly satisfying about the economy of the result. The theorem does not say the sphere is chaotic. It does not say most points must be bad. In fact, almost the entire sphere can carry a perfectly nice smooth field. The theorem asks for very little. Only that one cannot have everything. Only that somewhere, at least once, the field must yield. That small exception is enough to divide the possible from the impossible. This economy is part of what makes the result memorable. Mathematics often achieves its deepest effects not by adding complication, but by identifying the one simple thing that cannot be removed. On the sphere, it is the unavoidable zero. On the torus, that zero is no longer required. A single hole changes the story. A single missing possibility defines an entire class of fields. A single stubborn point reveals the whole topological nature of the surface. It is hard not to admire that level of efficiency. And perhaps that is why this theorem is so often remembered long after more technically complicated facts have faded. It gives the mind something it can hold. You can picture the ball. You can picture the comb. You can picture the one tuft that will not settle down. Then, once the image is secure, the mathematics begins to unfold underneath it. Directions become vectors. Hair becomes a tangent field. The tuft becomes a singularity. The grooming problem becomes a topological obstruction. The Earth itself becomes an example. By the time you have reached the deeper theory, the original image is still there, patiently keeping the whole structure intuitive. That combination is rare and valuable. It means the theorem can be entered from many directions. A person who likes geometry can enjoy the structure of the surface. A physicist can think about fields and flows. A meteorologist can picture calm points and global wind patterns. A student can remember the image long enough for the formal statement to become natural. Even someone who does not care much for mathematics in the abstract may still find the central fact strangely convincing once it has been attached to such a concrete and ridiculous picture. There is also a gentle lesson here about what it means to understand a mathematical truth. Understanding is not only being able to repeat the statement. It is not only knowing that the theorem says a continuous tangent vector field on a sphere must vanish somewhere. That is the formal sentence, and it matters. But real understanding comes when you can feel why the statement belongs to the sphere, why the torus escapes, why local flatness does not rescue global smoothness, and why the singularity is not a bug in the construction, but a necessary part of the whole. By that standard, the hairy ball theorem is an excellent teacher. It begins with image, moves into structure, and ends with a more mature kind of intuition. At first, you merely believe the ball must keep one bad spot. Later, you understand that the bad spot is the visible trace of a global invariant. By the time you really know the theorem, the cowlick has become something much more dignified than it sounded at the beginning. Still, the original image deserves to survive all the way to the end because it keeps the theorem honest. Without it, the result risks floating upward into elegant but forgettable abstraction. With it, the theorem remains attached to the ordinary physical world of surfaces and directions, and the stubborn fact that some patterns cannot be completed, no matter how carefully one tries. Hair is funny, yes, but it is also the reason the theorem remains alive in the imagination. And imagination matters more in mathematics than people sometimes admit. Not because proof is optional, obviously, it is not. But because the best ideas are usually first grasped through a picture, a motion, a tension, or a small physical intuition that carries the abstract content in human form. We understand first with the hand and the eye, then with formal language. The hairy ball theorem understands this perfectly. It arrives wearing a joke and leaves behind a piece of topology. By now one can see the shape of the whole story rather clearly. A surface is not just a shape to look at. It is a place that may or may not allow certain smooth global structures. A vector field is not merely a collection of arrows. It is a test of what the surface can support. A singularity is not just a point where the field fails. It is the place where the topological truth becomes visible. And topology itself is not merely classification for its own sake. It is the study of the deep features of shape that decide what kinds of order are possible. That is a rather good return from one little theorem. It is also worth noticing that the theorem never needed to become grand or dramatic to matter. It did not require hidden dimensions, exotic physics, or impossible scales. It lived on a familiar surface. It asked a simple question. It gave a clean answer. And from that answer, a wider view of mathematics opened almost by itself. There is something reassuring in that. It suggests that depth in mathematics does not always arrive through intimidation. Sometimes it arrives through patience. You stay with a small question long enough, and it begins to reveal the larger architecture around it. So what is the final lesson here? Perhaps it is this. Perfect smoothness across a whole system is sometimes impossible for reasons that no local inspection will reveal. The shape of the whole matters. The global structure matters. The places where order breaks are often the places where truth becomes visible. And what looks at first like a defect may in fact be the most faithful expression of the underlying mathematics. That is not a dramatic lesson, but it is a durable one. It applies to this theorem certainly. It applies to many other parts of mathematics. It applies to science whenever fields, flows, or orientations meet the topology of the spaces they inhabit, and it leaves behind a very practical intellectual habit. When something refuses to flatten out completely, do not ask only what went wrong. Ask what kind of surface you're standing on. Because sometimes the answer is not that you've made a mistake. Sometimes the answer is that the world, very quietly, has a rule, and the sphere is one of the clearest places where that rule can be seen. It lets you smooth almost everything. It invites confidence. It rewards local effort. Then, at one unavoidable point, it reminds you that completeness has limits. The hair will lie down nearly everywhere. The field will behave beautifully over most of the surface. The pattern will come very close to perfection. But somewhere, one small region keeps its independence, not out of spite, not out of messiness, simply because that is what the sphere is. So if you imagine the theorem one last time, do not picture failure, picture honesty. A smooth surface carrying as much order as it can, and one necessary place where the order stops pretending it can be total. One last strand refusing to lie flat, not because the comb was careless, but because topology asked it not to. And that, really, is why the theorem stays with people. It takes a simple act, a familiar object, and an almost childish image, and uses them to say something exact about the limits of smoothness in a shaped world. It says that some arrangements are forbidden not by lack of effort, but by the structure of reality. It says that form is never only decoration. It says that even the neatest pattern may be required to keep one truthful interruption. If you have followed this strange little path from hair to weather to vector fields to topology, then you are now slightly farther along your own evening than when we began, carrying perhaps one more theorem than you had before, and certainly one more reason to look suspiciously at a tennis ball. And if, somewhere in the quiet drift of all this, the idea settled into place without needing to be forced, then the theorem has done exactly what good mathematics does. It has taken something that first sounded absurd and left it feeling inevitable. So wherever you're listening from, and whatever hour it has become in your part of the world, I hope this uncombed sphere has been pleasant company. The theorem will still be there tomorrow, keeping its one necessary cowlick, asking the same clean question of every sphere that comes along. And the answer, just as quietly as before, will remain the same. Some things can never lie flat.